What if I told you that everything, every galaxy, every star, every planet, and even you, can trace its origins back to clouds so cold, so dark, and so empty, they were almost nothing at all? Long before the first star flickered in the void, before galaxies spun into elegant spirals, and before light even had a source, the universe was ruled by ancient, invisible giants, primordial gas clouds. These colossal structures were made of the simplest elements, yet they held within them the power to shape everything we now see in the cosmos. They were silent, unseen, and forgotten, until now. In this video, we're going to uncover one of the greatest and most overlooked space mysteries of all time, the haunting story of the universe's first breath, born not in brilliance, but in stillness. This is the untold story of the primordial gas clouds, the true architects of the cosmos. But before we continue, subscribe to the channel so you don't miss out on any of these videos. To understand primordial gas clouds, we must rewind the cosmic clock all the way back to the Big Bang, roughly 13.8 billion years ago. In the earliest seconds of existence, the universe was unimaginably hot and dense, so hot that atoms couldn't even exist. Instead, it was filled with a soup of subatomic particles, quarks, electrons, photons, and neutrinos, colliding and bouncing at relativistic speeds. As the universe expanded, it cooled. Within minutes, a process known as Big Bang nucleosynthesis took place, where the first nuclei of hydrogen, helium, and trace amounts of lithium were formed. But atoms wouldn't emerge until about 380,000 years later, during the epoch called recombination. That's when electrons finally cooled down enough to combine with these nuclei, forming the first neutral atoms. And that's when the primordial gas clouds were born. These clouds weren't clouds in the way we think of them on Earth. They were vast, diffuse regions of hydrogen and helium gas, spread across the cosmos in uneven clumps. These clumps formed because of tiny fluctuations in the density of matter, fluctuations imprinted by quantum irregularities that had been stretched out during cosmic inflation. Over time, gravity started pulling matter into these fluctuations, slowly forming filaments, knots, and voids in a cosmic web. The densest regions within this web would eventually collapse to form stars and galaxies. But before that happened, they existed as vast, cold gas clouds. They are the link between the universe's dark, post-recombination age and the birth of the first luminous objects. But here lies the mystery. These gas clouds are made mostly of neutral hydrogen, and neutral hydrogen doesn't emit light in the visible spectrum. That's why the period after recombination is often referred to as the cosmic dark ages, an era before the first stars ignited, where the universe was filled with darkness and invisible matter. If you had a spacecraft and could travel back to that time, you wouldn't see galaxies or stars or even light, just vast regions of nothingness, except that the nothingness was actually everything. Detecting these clouds is extremely difficult. They don't emit visible light. The only clue we have comes from a very specific phenomenon, the 21 centimeter hydrogen line. This is a very faint signal produced when the electron in a hydrogen atom flips its spin direction. It's an incredibly rare event, but when it happens across vast amounts of hydrogen, the cumulative effect is measurable. By detecting the 21 centimeters line from across the cosmos, astronomers are now trying to map the distribution of primordial gas clouds. This is a challenge requiring radio telescopes of immense sensitivity, instruments like the Square Kilometer Array, SK, and the Hydrogen Epoch of Reionization Array, HERA. These facilities are our only hope of painting a picture of the universe before stars. But there's another problem. After the formation of the first stars, known as population 3 stars, something dramatic happened: reionization. These first stars were massive and short-lived, emitting intense ultraviolet radiation. This radiation ionized the surrounding hydrogen gas, breaking apart the neutral atoms and making the gas clouds glow faintly. This marks the end of the cosmic dark ages. So if we want to observe truly primordial gas clouds, those that existed before any star ignited, we need to detect hydrogen that hasn't yet been disturbed by stellar radiation. That means looking back to a time before the first lights switched on, which pushes the limits of our observational capabilities to the extreme. These clouds exist in a narrow window, after recombination, but before reionization, a sliver of cosmic time known as the Dark Ages. And that's why they're so mysterious. They are not just ancient, they are inaccessible, hidden behind a veil of time, space, and physics. Yet they are essential. Without them, stars could not form. You see, for a star to ignite, gas must collapse under gravity to form a dense core. But collapsing gas heats up, and if it heats up too much, pressure resists further collapse. In the modern universe, this problem is solved by heavy elements, carbon, oxygen, and dust, that help radiate away the heat. But in the early universe, these didn't exist. Primordial gas clouds contained only hydrogen and helium. That means the physics of their collapse was different. The gas had to find other ways to cool, mainly through molecular hydrogen, a rare but vital component in early cloud formation. The efficiency of this cooling dictated how fast and how large the first stars could form. And those first stars, in turn, shaped the entire architecture of the cosmos. Population 3 stars likely formed in the densest regions of these gas clouds, shining briefly before exploding as supernovae and enriching the surrounding space with heavier elements, what we call metals in astrophysics. From those metals, the next generations of stars, Pop 2 and eventually Pop I, like our Sun, would emerge. But what happened to the gas clouds that never formed stars? Some of them likely remained as invisible, diffuse wisps, slowly falling into the gravitational wells of galaxies. Others may have become absorbed into dark matter halos, where they persist today as cold reservoirs of gas in the circumgalactic medium, that strange, half-lit space surrounding galaxies like a ghostly halo. In fact, some primordial gas clouds might still exist today. In recent years, astronomers have discovered a few strange objects, known as Lyman alpha blobs, that might be modern relics of primordial gas. These are vast clouds of hydrogen, hundreds of thousands of light years across, glowing faintly in ultraviolet light. No stars. No galaxies. Just glowing gas. There are also observations of metal-free absorption lines in the spectra of distant quasars, suggesting the presence of pristine gas clouds with no trace of star formation. These clouds may be the unprocessed leftovers from the Big Bang, untouched by the nuclear furnaces of stars. That means these clouds could hold the purest material in the universe, a direct sample of the early cosmos before anything complex or structured ever emerged. Studying them is like finding a cosmic fossil, untouched by time, hidden in the shadows of the universe. And here's the twist: they may be the key to solving the mystery of dark matter and dark energy. How? Because the way these clouds move, collapse, and interact with surrounding matter is influenced by gravity. If we can map them accurately, we can infer the presence of invisible mass, that is, dark matter. Some theories even suggest that variations in the distribution of these clouds could be used to detect the imprint of dark energy on the expansion of the early universe. So these clouds, silent, invisible, ancient, are not just the starting point of the universe's story. They are the silent witnesses of its deepest mysteries. Let us now dive deeper into the veiled world of these ancient cosmic specters, because the more we learn about primordial gas clouds, the more we realize they are not just relics of the past. They are active participants in the cosmic dance, influencing events across time in subtle, astonishing ways. The question now becomes, how exactly do we detect these elusive clouds across the vast gulfs of time and space? As mentioned earlier, the 21-centimeter line of neutral hydrogen is our most promising tool. However, this signal is incredibly faint, far weaker than almost anything else in the sky. To detect it, we need massive, carefully shielded radio telescopes that can block out interference from Earth and even our galaxy. The Hydrogen Epoch of Reionization Array, HERA, in South Africa and the Future Square Kilometre Array, SKA, in Australia are specifically being designed to chart these faint whispers from the early universe. But detecting them isn't as simple as tuning into a cosmic radio station. Because the universe is expanding, the wavelength of this 21-centimeter signal is redshifted, stretched into longer and longer wavelengths as it travels across time. The farther away, and thus older the cloud, the more stretched its signal becomes. By measuring the redshift, we can essentially look back in time and map the evolution of gas clouds across cosmic history, from the Dark Ages to the dawn of galaxies. Yet, there's another intriguing method scientists use, one that turns distant quasars into cosmic lanterns. Quasars, which are incredibly bright cores of distant galaxies powered by supermassive black holes, emit light that travels billions of years to reach us. As this light passes through primordial gas clouds on its journey, specific wavelengths are absorbed by the hydrogen in those clouds. This creates a pattern of absorption lines known as the Lyman alpha forest. Each dip in the spectrum corresponds to a different cloud the light has passed through, each at a slightly different redshift. It's like looking at a barcode of the early universe, with each line representing a gas cloud that once drifted silently in the vast, black void. This forest of lines is one of our most powerful windows into the otherwise invisible structure of the early cosmos. The Lyman alpha forest doesn't just tell us where gas clouds are, it tells us about their temperature, density, and chemical composition. Most importantly, it helps distinguish truly primordial clouds, those made only of hydrogen and helium, from more recent clouds enriched by the products of star formation. But the story becomes even more fascinating when we consider the role of dark matter in shaping these clouds. Primordial gas clouds didn't form in isolation. They were guided, tugged, and molded by the invisible scaffolding of dark matter halos. These halos are concentrations of dark matter, an unknown substance that doesn't emit or absorb light, but which exerts gravitational pull. It's believed that every galaxy formed within a dark matter halo. And before galaxies existed, gas clouds were already pooling into these gravitational wells. Without dark matter, the universe wouldn't have had enough structure to form stars and galaxies by the time we see them in today's universe. Primordial gas clouds were essentially tracers of dark matter, flowing into its gravity wells and collecting into the earliest nodes of structure. If we can detect and trace the distribution of these clouds, we can also begin to map the invisible dark matter framework of the universe. But here's something even more profound. Some primordial gas clouds may never have collapsed into stars at all. These untouched clouds, often referred to as mini-halos, are cosmic fossils that never underwent star formation. They drift in isolation, their hydrogen and helium atoms as pristine as they were after recombination. If we could find and study one of these untouched clouds directly, it would be like reaching back into the womb of the cosmos and touching the fabric of its earliest matter. However, finding them is immensely difficult. They're cold. They're invisible. And unlike other cosmic structures, they have no light of their own. Only their gravitational effects, their impact on quasar light, or their faint radio signatures can betray their presence. They're the ghosts of creation, hiding in the shadows of time. In recent years, there have been a few tantalizing discoveries. Astronomers using the Keck Observatory in Hawaii observed a gas cloud with no detectable metals, no carbon, oxygen, or iron, suggesting it had never been polluted by stellar processes. This cloud may have been unprocessed since the Big Bang. If confirmed, it would be one of the purest pieces of the universe ever discovered. Other discoveries include dark galaxies, gas-rich objects with little to no stars. These are theorized to be failed galaxies, where the gas never reached the conditions needed to ignite star formation. Could they be evolved descendants of primordial gas clouds that somehow dodged the galactic evolutionary path? Possibly. There's even more mystery surrounding how these gas clouds contributed to the process known as reionization, the cosmic event where ultraviolet light from the first stars reionized the neutral hydrogen across the universe. This process, which occurred between 500 million to 1 billion years after the Big Bang, effectively turned the universe from opaque to transparent again. Primordial gas clouds played a central role in this transformation. As the first stars formed inside them, their light began carving out ionized bubbles in the surrounding darkness. These bubbles expanded, collided, and eventually reionized the entire cosmos. But the precise timeline and sequence of this reionization is still hotly debated. Were the first stars the main drivers of reionization, or did black holes and quasars contribute significantly? Did some gas clouds survive the reionization untouched, remaining pristine until now? These are questions researchers are actively pursuing. And beyond all of this, there is one final enigma. Could these primordial gas clouds hold the key to new physics? Some theories suggest that the formation and distribution of these clouds could be sensitive to variations in fundamental constants, such as the fine structure constant or the mass of the electron. Others propose that exotic particles, like sterile neutrinos or axions, might have subtly altered the thermal history of the universe, leaving imprints in the distribution of these clouds. If such anomalies could be detected in the hydrogen absorption signals, it might point us to new laws of nature. Even more radically, some researchers have proposed that the apparent absence or presence of certain types of clouds in specific regions could hint at the existence of multiple universes, a multiverse, each with slightly different physical parameters. While this remains speculative, the idea that gas clouds could offer clues to the larger reality beyond our observable cosmos is mind-bending. What we know is this: primordial gas clouds are not just the raw materials of stars and galaxies. They are the original code of the cosmos, unaltered and undeciphered, drifting through time with secrets we are only just beginning to understand. As our instruments grow more powerful and our theories more refined, we may one day unlock the full story of these ancient sentinels. Until then, they remain one of the greatest and most profound mysteries of space, the invisible breath of the universe before the first heartbeat of light. As we continue to delve into the cosmic saga of primordial gas clouds, we find ourselves standing at the threshold between observable science and the deepest philosophical questions about our origin. These clouds, vast, cold, and ancient, represent a bridge between what was and what is. They are not just matter, they are memory. A memory of a time before stars illuminated the darkness, before galaxies swirled into being, before even the concept of time as we understand it took root in the fabric of space-time. To fully appreciate their place in the universe, we must revisit the concept of cosmic structure formation. After the Big Bang and the recombination epoch, the universe became neutral and transparent. It was filled with a nearly uniform sea of hydrogen and helium, but seeded with tiny variations in density, mere 1 in 100,000 differences, caused by quantum fluctuations during the inflationary period. These minuscule irregularities were enough. Over time, gravity amplified these seeds, pulling matter into clumps that would become the earliest gas clouds. It wasn't an explosive process. It was slow, patient, and precise. Over tens of millions of years, these overdense regions grew denser, forming what we now call dark matter halos. The primordial gas clouds that fell into these halos began to cool and contract. And it is within these densest parts of the early universe that the first stars were born. But what of the clouds that never became dense enough? What about those that floated freely in the voids between structure, never achieving the mass necessary for gravitational collapse? Many of these clouds likely still exist, undisturbed and invisible, floating in the cosmic web like cosmic plankton in a dark, endless ocean. Detecting them is difficult because, unlike stars or galaxies, they don't emit or reflect light. They are not merely dark, they are non-luminous, silent voids of potential. But science is catching up. A major development in recent cosmology is the attempt to conduct 21 centimeters tomography of the early universe. This is the radio equivalent of a CAT scan. By capturing 21 centimeters radio signals from different regions of the sky at different redshifts, astronomers can build a three-dimensional map of the distribution of neutral hydrogen over cosmic time. It's not an image in the traditional sense. It's more like a volume of shadows, from which structure, voids, and filaments can be inferred. This method is not without its challenges. Earth-based radio telescopes face serious interference from our own civilization, cell phones, satellites, radio stations. Even the atmosphere itself can distort these faint signals. That's why some have proposed placing radio telescopes on the far side of the moon, permanently shielded from Earth's noise. A lunar observatory could give us an unprecedented view of the untouched universe, perhaps even allowing us to detect individual primordial clouds for the first time. Imagine that. A telescope, hidden from Earth's noise, peering into the earliest chapters of the cosmos and revealing the first traces of form in a formless universe. It would be like hearing the first whisper after an eternity of silence. Meanwhile, space-based observatories like JWST, James Webb Space Telescope, are looking for the earliest galaxies, some of which may have formed directly from the collapse of primordial gas clouds. Already, JWST has challenged previous timelines by spotting bright, well-formed galaxies far earlier than expected, some less than 300 million years after the Big Bang. That rapid appearance suggests that the first gas clouds collapsed into stars and galaxies more quickly than our models predicted. Could this mean our understanding of gas cloud behavior is flawed? Possibly. It could indicate that primordial gas clouds were more efficient at cooling and collapsing than we thought. Or it might suggest the presence of unknown physics at play during those early moments. Cooling is key here. In modern galaxies, cooling is facilitated by metals, carbon, oxygen, nitrogen, which help radiate away heat. But in the primordial universe, the only coolant available was molecular hydrogen, H2, which forms only under specific, fragile conditions. If something disrupted the formation of H2, say, intense ultraviolet radiation from nearby protogalaxies, it could prevent clouds from collapsing and forming stars. This introduces the concept of feedback mechanisms, processes where early stars and galaxies influence the formation of others. For instance, the intense light from the first population 3 stars could ionize nearby gas clouds, preventing their collapse, effectively halting star formation in their vicinity. This intercloud interaction means that primordial gas clouds weren't just passive, they were part of a dynamic, interactive environment where some succeeded and others failed to birth light. Some clouds, however, may have been large enough to resist disruption. The most massive gas clouds could absorb the shock of ionizing radiation and continue their collapse, forming what we believe were supermassive stars, hundreds of times more massive than our Sun. These stars lived short, brilliant lives, ending in either parent stability supernovae or direct collapse into black holes, possibly even forming the seeds of supermassive black holes we see at the centers of galaxies today. Yes, you heard that right. It's possible that the first supermassive black holes, those mysterious monsters billions of times the mass of the Sun, originated from the collapse of the densest primordial gas clouds. But what about the clouds that didn't collapse? What about those that floated, eternally diffuse, unignited and unilluminated? It is entirely plausible that some of these clouds drifted along with the expansion of the universe, only slowly falling into the halos of forming galaxies. In doing so, they may have become part of a galaxy's circumgalactic medium, CGM, the vast halo of gas that surrounds galaxies like a cocoon. These clouds act as reservoirs of fuel, feeding galaxies over billions of years. Interestingly, when astronomers observe distant galaxies, they often see signs of these surrounding gas reservoirs. Absorption spectroscopy allows them to detect clouds passing in front of background light sources, even if those clouds emit no light of their own. Many of these clouds show low metallicity, suggesting they are remnants of the primordial universe, still relatively unpolluted. And here's the fascinating twist. Some simulations suggest that certain clouds within the CGM may have survived since the early universe, avoiding star formation for over 13 billion years. If these are indeed ancient, untouched clouds, they represent cosmic time capsules, preserving the conditions of the early universe and their chemical makeup. But there's a more speculative and thrilling possibility. What if some primordial gas clouds formed stars, but not the kind we're familiar with? There are theoretical models of dark stars, not made of nuclear fusion, but powered by the annihilation of dark matter particles. In regions of high dark matter density, like the centers of early halos, it's possible that dark matter could interact with regular matter in such a way that it heats the cloud from within, preventing collapse but creating a stable structure. These dark stars would be enormous, cool, and invisible in the traditional sense, but they could exist for long periods of time, eventually collapsing into black holes. If such stars existed, then primordial gas clouds might have birthed objects that never emitted light, but still profoundly influenced cosmic evolution. And if those objects still exist today, they may explain some of the missing mass and missing light in the universe, one of the enduring puzzles of modern astrophysics. As we continue to refine our instruments, conduct deep sky surveys, and run ever more sophisticated simulations, we inch closer to unveiling the true nature of these primordial clouds. They are not just background noise or incidental features, they are foundational. They are the first architectures of structure, the blueprints from which everything we know was built. And perhaps, buried within them, lies the ultimate answer to the most profound question of all: why does anything exist at all? Because to understand primordial gas clouds is to understand how the universe transformed from a formless, chaotic energy soup into a structured cosmos, filled with galaxies, stars, planets, and life. These clouds mark the moment potential became reality. They are the threshold between nothing and everything. And they are still out there, drifting, waiting for us to find them. So we press forward, guided by radio waves, spectral signatures, and the imagination of cosmologists who envision the silent choreography of hydrogen atoms in an untouched void. As we reflect on the fate of these primordial gas clouds, we realize that they are not merely dead ends in cosmic evolution. On the contrary, they are keys, unlocking fundamental truths about how complexity arises from simplicity and how the universe orchestrates matter into form. One especially important aspect lies in the role of turbulence and fragmentation within these clouds. In the cold, dark depths of intergalactic space, one might assume everything is calm and still. But primordial gas clouds were anything but static. Even in the absence of stars, supernovae, or galactic dynamics, these clouds were shaped by turbulent motions, driven by gravitational instabilities and the surrounding flows of the expanding universe. As these clouds accreted into dark matter halos, they didn't form neat, uniform structures. They fragmented, splintering into denser and less dense regions. In modern star-forming clouds, fragmentation often leads to clusters of stars. But in primordial gas clouds, fragmentation was more primitive, governed entirely by the physics of hydrogen and helium cooling. The chemistry was minimal, but the outcomes were monumental. In some regions, cooling was efficient enough that the gas collapsed into singular massive clumps, leading to the first population 3 stars, massive beacons of light that burned hot and died fast. In other regions, the fragmentation may have been so slow or incomplete that the clouds simply hovered on the edge of collapse, neither forming stars nor dissipating, suspended in a kind of cosmic limbo for billions of years. But here's where the story becomes astonishing. Some of these clouds may still exist today, unchanged since the universe was a few 100 million years old. Let's pause on that. Imagine a structure in the cosmos, untouched for over 13 billion years. Not a star, not a planet, not even dust, just a wispy, diffuse cloud of gas, adrift in space, its atoms still holding the precise imprint of the conditions from the dawn of time. It would be the oldest physical structure in the universe, older than any galaxy, any star, any black hole. And it would hold answers to questions we haven't even thought to ask. Could such clouds serve as laboratories for probing the constancy of physical laws? Could we use them to test whether the fundamental constants, like the speed of light or the strength of gravity, have changed over time? Some physicists believe they might. Tiny variations in the absorption lines of ancient gas clouds could hint at shifts in the fine structure constant or the electron-to-proton mass ratio, subtle, almost imperceptible changes that would rock the foundations of modern physics. It's as if these clouds don't just whisper history, they whisper cosmic law. And yet, despite their potential, these clouds remain elusive. We've detected hints: cold gas with low metallicity, unusual hydrogen absorption signals, and even radio shadows, but no definitive map exists of all the primordial gas clouds that should be out there. Why? One possibility is that they were erased by reionization. During the epoch of reionization, when ultraviolet light from early stars and galaxies began to sweep across the cosmos, much of the neutral hydrogen was ionized. This radiation would have torn electrons from atoms, breaking apart many low-mass gas clouds before they could ever form stars. Only the densest or most shielded clouds may have survived. This process effectively burned away large regions of the early universe, making surviving clouds incredibly rare and precious. The clouds that did endure must have hidden in cosmic voids, far from the action, places where light from early galaxies never reached, or where shielding by surrounding structures preserved their delicate state. And those are precisely the regions we must now search. Today, sophisticated cosmological simulations, such as Illustris, Eagle, and Renaissance, are helping us trace where these clouds might exist. These simulations incorporate the physics of dark matter, gravity, thermodynamics, radiation feedback, and cosmic expansion to predict where primordial gas clouds should have formed, and where remnants might still be found. By comparing these predictions with observational data from radio and optical telescopes, scientists are zeroing in on target zones for exploration. And the mystery deepens when we ask, could these clouds have played a role in planet formation? At first, it seems absurd. After all, planets require metals, and primordial gas clouds have none. But there is a hypothesis, still speculative, but fascinating, that says some population 3 stars may have formed short-lived protoplanetary disks, even in metal-free environments. These disks wouldn't form rocky planets like Earth, but gas giants, perhaps made of pure hydrogen and helium. Such objects, ejected from their systems, could now be wandering the galaxy as rogue planets, completely invisible to detection unless they pass in front of a star. If that's true, then primordial gas clouds didn't just seed galaxies and stars. They may have seeded entire populations of dark, ancient planets, ghosts of a time before elements. The implications are staggering. And as we consider those implications, we begin to realize something profound. Primordial gas clouds were never just clouds. They were cosmic incubators, quiet alchemists that slowly turned potential into structure, order, and beauty. Every galaxy began with a cloud. Every star began with a cloud. Every planet, every molecule, every story, began with a cloud. And now, billions of years later, here we are, thinking beings made of stardust, looking back through the telescope, trying to trace our existence to the very first breath of matter. In this sense, the study of primordial gas clouds is not merely astrophysics, it is cosmic anthropology. It is the act of reaching back through time and space to understand where we came from, and how the universe allowed life, thought, and wonder to arise from a sea of particles. There's still so much to learn. Are we missing populations of primordial clouds because they lie in regions beyond our detection limits? Are there types of clouds we haven't even theorized yet, those dominated by exotic particles, or embedded within cosmic strings or topological defects left over from the Big Bang? Could some clouds serve as cradles for entirely different forms of structure, perhaps never forming stars, but something else entirely, something we haven't imagined? And if these clouds are still drifting in the deep intergalactic medium, will future space missions finally be able to isolate one, measure it, analyze its composition in detail, and perhaps listen to what it's been trying to tell us for 13.7 billion years? The journey isn't over. We stand at the edge of a discovery that could redefine our understanding of cosmic history, elemental evolution, and the very fabric of the universe itself. Primordial gas clouds are not just ancient. They are timeless. Their legacy lives on in every atom of your body, in every beam of starlight, and in the mysterious forces that still shape the cosmos today. They are the first breath of creation, and they may yet have the final word. As our journey into the realm of primordial gas clouds deepens, we come to realize that they are far more than just ancient leftovers of the early universe. They are active participants in the story of cosmic evolution, dynamic players whose influence echoes across billions of years. To study them is to reach back to the cosmic dawn, to witness the raw scaffolding of the cosmos, and to glimpse the moment when structure first began to assert itself over chaos. Let us now consider their interaction with dark matter, a substance that outweighs normal matter by a factor of about 5 and yet eludes direct detection. Dark matter doesn't interact electromagnetically, so it doesn't emit or absorb light. But it exerts gravitational influence, and this influence was critical in drawing together the first primordial gas clouds. Without dark matter, it's likely the universe would still be a diffuse, featureless expanse. Gravity alone, from baryonic matter, wouldn't have been enough to seed structure as quickly as we observe it. Cosmological simulations suggest that dark matter halos formed first, collapsing under their own gravity. These halos then acted as gravitational wells, drawing in the surrounding hydrogen and helium gas. The result: dense pockets of gas forming at the centers of these halos. In essence, primordial gas clouds were guided into shape by invisible hands, wrapped in the unseen skeleton of dark matter. This also means that where we find primordial gas clouds, or their remnants, we might also be tracing the distribution of dark matter itself. Some have even proposed that studying the behavior and motion of such clouds could help us map dark matter more precisely than through galaxy rotation curves or gravitational lensing. If we can observe clouds that are not yet influenced by the feedback mechanisms of galaxies, no supernovae, no black holes, then we're seeing the purest gravitational interactions between baryonic matter and dark matter that the cosmos has to offer. This makes these clouds natural laboratories not only for understanding the early universe but also for testing our theories of gravity and dark matter behavior. Some alternate models, such as modified Newtonian dynamics, MOND, or theories involving warm or fuzzy dark matter, suggest different behavior in the early universe. These theories often make different predictions about how small structures, like primordial gas clouds, form and evolve. Observing a large population of such clouds could therefore serve as a crucial test between competing cosmological theories. It could even hint at entirely new physics, forces or particles we haven't yet detected but which shape the very formation of structure at the smallest scales. Yet these clouds are also intertwined with larger-scale cosmic phenomena, such as the cosmic web. When we look at simulations of the universe, we don't see a random smattering of matter. Instead, we see a filamentary structure, a vast, interconnected network of threads and nodes composed of galaxies, dark matter, and gas. This web formed as matter collapsed along sheets and filaments under the influence of gravity. What's fascinating is that primordial gas clouds helped to outline this structure. As gas flowed along the filaments, it fed into forming galaxies and clusters. But in the lower density regions, between the filaments, some gas remained relatively untouched, forming isolated clouds that still exist today as part of the intergalactic medium or cosmic voids. In these voids, shielded from the chaotic energies of star formation and supernova feedback, some clouds could have survived almost completely unchanged for billions of years. These clouds are so tenuous, so diffuse, that even detecting them requires extreme precision, looking for tiny absorption features in the light of distant quasars or gamma-ray bursts. And yet, every one we detect is like finding a fossil, a relic from a time when the universe was dark and silent, before the light of the first stars began to burn. The chemical composition of these clouds also tells us a great deal. Primordial clouds contain only hydrogen and helium, with minute traces of deuterium and lithium, the only elements produced in significant amounts during Big Bang nucleosynthesis. There are no heavier elements, no carbon, no oxygen, no iron. That means any cloud we find that shows a lack of metallicity is potentially a true relic from the earliest times. These clouds help astronomers verify and constrain models of Big Bang nucleosynthesis, offering a window into the conditions that existed in the first 3 minutes of the universe's life. If we find a cloud that deviates from the expected ratios of hydrogen to deuterium or helium, it could point to new physics in the early universe, such as the presence of unknown particles, changes in the expansion rate, or even exotic energy fields. But while most primordial gas clouds drifted aimlessly through space, a few may have encountered something remarkable: primordial black holes. These hypothetical black holes, potentially formed in the high-density fluctuations of the early universe, could have passed through gas clouds, disrupting them, or even gathering them like seeds gather snow. Some theorists suggest that the accretion of gas onto primordial black holes in the early universe may have been the source of mysterious phenomena like the Lyman alpha blobs, enormous, glowing clouds of hydrogen that span hundreds of thousands of light years, with no obvious source of illumination. Or consider this: could primordial gas clouds have been trapped around black holes for billions of years, slowly spiraling inward, feeding them so gently that no radiation was released, a process called radiatively inefficient accretion? If so, then many black holes, seemingly inactive, may still be slowly devouring clouds left over from the dawn of time. Now let's zoom forward in time. In the present-day universe, large spiral and elliptical galaxies like the Milky Way are surrounded by halos of gas, often extending hundreds of thousands of light-years into space. Some of this gas is recycled material from galactic winds or supernova ejecta, but some may be ancient, leftover gas that never formed stars, never mixed with metals, and still carries the pristine fingerprint of the early universe. Astronomers call these regions the circumgalactic medium, CGM. When studied closely, especially using quasar absorption lines, the CGM reveals a complex mix of old and new gas. In rare cases, the composition points to a low metallicity origin, consistent with primordial gas. These clouds, still in orbit, still cold, still waiting, might one day spiral inward, giving rise to new generations of stars, even now. So the story of primordial gas clouds isn't just past, it's also future. These clouds may still play a role in star formation today. Galaxies undergoing rejuvenation, such as low-surface brightness galaxies or those experiencing unexpected starbursts, may be tapping into ancient gas reservoirs that lay dormant for billions of years. It's a cosmic second chance, a reawakening of material that was never used in the first great epoch of star formation. And then there are the rogue clouds, high-velocity clouds moving at hundreds of kilometers per second through galactic halos. Some of these are believed to be debris from galactic interactions or supernova-driven winds, but others may be entirely unassociated with any known structure. Where did they come from? Could they be primordial fragments, drifting alone for eons, finally intersecting the gravitational domain of a galaxy? Their origin is a mystery, and in their mystery lies our opportunity. With upcoming missions like the Square Kilometre Array, SKA, LUVOIR, and next-gen space telescopes, astronomers hope to detect more of these elusive clouds, not just statistically, but directly. The SKA, with its unprecedented sensitivity to radio signals, may be able to map hydrogen at cosmic dawn, identifying where the first clouds coalesced. And LUVOIR, with its deep UV sensitivity, might find new absorption features in quasar light, revealing clouds that other telescopes missed. Each discovery would be like adding a page to a book we thought had been lost, a sacred book titled The Birth of Everything. And perhaps, one day, we will isolate a single primordial gas cloud, untouched, untainted, perfect. We will study its atoms, its density profile, its motion, and its alignment with dark matter filaments. And in doing so, we will not just understand a cloud, we will understand the moment the universe began to build. A single cloud could be enough. Enough to validate our theories. Enough to falsify cherished models. Enough to revolutionize everything we know about the way structure arises from entropy. As we continue our journey through the mystery of primordial gas clouds, we must now linger on one of the most haunting truths about them, that they embody the most pristine and unaltered memory of the early cosmos. Every known structure in the universe, galaxies, stars, planets, even dust, has undergone processes of recycling and transformation. Stars explode and seed space with heavier elements, galaxies collide and evolve, and even interstellar gas is enriched with metallicity through countless generations of stellar life and death. But primordial gas clouds, if they remain untouched, are the only things that still exist in their original, cosmic infancy. To find one is to touch time itself. Their atoms were forged in the immediate aftermath of the Big Bang, when temperatures cooled just enough for protons and neutrons to form stable nuclei. Their structure was defined before any galaxy formed, before any light existed, before even the first star had a chance to ignite. They are the embodiment of a universe that had not yet decided what it would become, pregnant with potential but still suspended in silence. But these clouds do not simply exist as passive relics. Even in their simplicity, they hold within them the full blueprint of cosmic evolution. Every force that would eventually shape stars, black holes, and galaxies was already at play within them: gravity pulling atoms together, pressure resisting collapse, and quantum fluctuations seeded during inflation that introduced subtle irregularities in the density field. These irregularities determined where the clouds would form, how massive they would be, and when they would collapse. In a sense, primordial gas clouds were the testing ground for every natural law we take for granted today. The balance between gravity and pressure, the behavior of particles in low temperatures, the role of quantum noise, everything the universe would use to sculpt structure, it first tried in these clouds. They are like the universe's first sketchpad, where trial and error etched out the rules of creation itself. There is a surreal elegance in realizing that these clouds were invisible architects of galaxies. As the dark matter halos pulled them inward, and as fragmentation slowly began, the clouds did not always collapse into a single massive star. In some rare cases, they may have become proto-galaxies, the ancestors of the Milky Way, Andromeda, and every massive structure we now see in the observable universe. But those galaxies began not with disks, not with spirals or mergers, but with a single primordial cloud, floating in a dark halo, shaped only by hydrogen physics and the gravitational whispers of dark matter. Over time, as stars formed and died within these proto-galaxies, the metallicity increased, and the clouds themselves transformed, blending into the interstellar medium. But the ghost of the original cloud remained, its memory imprinted in the elemental ratios, in the orbital distribution of stars, in the very DNA of the galaxy's formation history. Even now, some regions within galactic halos still retain that low metallicity signature, a whisper from a time when only hydrogen and helium existed. This leads us to one of the most intriguing pursuits in modern cosmology, the detection of ultra-metalpure stars. These stars, often found in the galactic halo or in dwarf galaxies orbiting larger ones, are like stellar fossils. Their atmospheres contain almost no elements heavier than helium, suggesting that they formed from clouds that were barely enriched by earlier generations. Some of these stars contain metallicities less than 100,000th that of the Sun. That means the cloud from which they formed had likely been enriched by only one or two supernovae, or in some cases, perhaps none at all. These stars may have condensed directly out of primordial gas clouds, and if so, they are direct descendants of the very first matter. By studying them, we gain indirect access to the chemical fingerprint of the early universe. Their age, composition, and structure help us understand the fragmentation properties of the first gas clouds and the conditions necessary for low-mass star formation in the absence of metals. Yet even more fascinating is the possibility that some primordial clouds never formed stars at all. If the conditions were not quite right, if the cooling wasn't efficient enough, or the density never reached a critical threshold, then these clouds might have remained in a state of suspended animation for billions of years. They would neither ignite into light nor disperse into void. They would simply drift, isolated, ancient, and untouched. Imagine a cloud of hydrogen the size of a galaxy, as old as time, completely dark, and floating in intergalactic space. No galaxy near it, no radiation striking it, no stellar winds or supernovae to disturb it. These are the dark ghosts of creation, and they may still be out there, undetected by our instruments, because they emit no light and absorb no starlight. The only evidence of their existence might come in the form of tiny anomalies in the cosmic microwave background, or unusual absorption features in the spectra of distant quasars. And it is here, at the intersection of the theoretical and the observational, that our greatest challenge lies. Our instruments are improving. Telescopes like ALMA, JWST, and the upcoming ELT, Extremely Large Telescope, have already begun to push the limits of detection. They are capable of capturing light from the earliest galaxies, the first stars, even hints of reionization. But detecting primordial gas clouds themselves is still profoundly difficult. The clouds are cold, their emissions faint, and their environments sparse. They do not emit the bright ionized lines we see in star-forming regions. Instead, we must rely on indirect detection, such as the Lyman alpha forest, an intricate pattern of absorption lines in the light of background quasars. Each line represents a cloud of neutral hydrogen at a different redshift. By analyzing these lines in high resolution, astronomers can reconstruct the distribution and density of hydrogen in the early universe. Some of these lines may very well come from primordial gas clouds that have never formed stars and never been enriched with metals. But even the Lyman alpha forest has limitations. It only traces clouds that lie directly along the line of sight to a distant, bright source. The vast majority of the sky remains unprobed, and many clouds are simply never intersected by light. This is why future observatories, like radio interferometers tuned to the 21 cm line of neutral hydrogen, are so promising. Projects like the Square Kilometre Array, SK, and Hydrogen Epoch of Reionization Array, HERA, aim to map the distribution of hydrogen across vast regions of space. These maps could reveal not only the first galaxies and stars but also the cold, faint gas clouds that never cross the threshold into illumination. The 21 cm signal is a kind of cosmic whisper, so faint yet so ubiquitous, that it could fill in the blanks of our cosmic history with unprecedented precision. In contemplating these clouds, we also face deep philosophical questions. If primordial gas clouds are the most ancient physical structures in the universe, older than any star, galaxy, or black hole, then they represent a kind of cosmic purity. They are the closest thing we have to the raw, untouched matter that came straight from the Big Bang. Every atom within them has spent 13.8 billion years waiting, not decaying, not transforming, just existing. To encounter one would be to meet a piece of the universe that has remained unchanged since the beginning. What does that say about the nature of time? Of change? Of permanence in an ever-evolving cosmos? And what if, just what if, some of these clouds contain surprises we cannot yet fathom? We assume they are simple, that they contain only hydrogen and helium. But what if, deep within the densest regions, strange physics is occurring? Could dark matter interactions within these clouds create unusual phenomena, subtle temperature changes, particle annihilations, even hints of new forces? Could certain clouds harbor conditions so unique that they remain stable in ways we don't understand, resisting collapse not because of thermal pressure, but because of unknown quantum interactions? There are theories, still speculative, that propose some primordial clouds may have become Bose-Einstein condensates on a cosmological scale, macroscopic quantum objects made of cold, bosonic dark matter. These condensates would behave not like ordinary gas, but like coherent, wave-like fields, possibly influencing nearby structures in bizarre and counterintuitive ways. If such clouds exist, they would represent an entirely new state of cosmic matter, bridging the gap between particle physics and astrophysics in ways we've never observed. And so, we are left in awe. Not because primordial gas clouds are flashy, or violent, or bright, but because they are the first breath of complexity, the moment when the universe began to wake up. Every cloud was a coin toss between collapse and stasis, between star birth and cosmic solitude. And every one of those outcomes fed into the next chapter of existence. They are quiet, but they are profound. They are ancient, but they are still with us. And if we listen closely enough, they may yet speak the final truths of the cosmos. There is a strange poetry in the fact that the most foundational components of cosmic structure are also the quietest. Primordial gas clouds are not the blazingly radiant galaxies that populate our telescopic images, nor the dramatic explosions of supernovae, or the wild spirals of accretion disks around black holes. They are dim, cold, quiet. But in that silence lies a story more powerful than almost any other, the birth of order from nothingness. Before stars sang their thermonuclear songs, before gravity stitched the cosmic web, before even the first light graced the pitch-black stage of the universe, these clouds drifted as the pure, featureless essence of all that was possible. Their simplicity was not emptiness, it was potential, and it shaped everything that came after. As time moved forward in the young universe, these primordial gas clouds began to feel the slow pull of gravity. Initially, this was a gentle nudge, not a dramatic collapse. The universe was still expanding rapidly, and only the densest pockets, those that lay within the seeds of dark matter halos, could overcome the tug-of-war between expansion and collapse. In those places, hydrogen atoms began to accumulate, building up over millions of years. The temperature was still too high for stars to form, but slowly, as more gas collected, something extraordinary began to happen. The gas began to cool. But this cooling was not like the radiative cooling we know from later, metal-enriched gas. This was cooling through molecular hydrogen, a much less efficient and more fragile process, which was the only cooling mechanism available in a metal-free universe. It was a delicate balance. The gas needed to cool to collapse, but molecular hydrogen was easily destroyed by even the faintest radiation. The survival and function of molecular hydrogen determined whether the cloud would proceed towards star formation or remain in stasis for eons. When cooling succeeded and densities rose, the center of the cloud would reach the so-called Jeans instability threshold, named after physicist James Jeans, beyond which gravity overtakes internal pressure. The gas would fragment, not into many stars as happens today, but often into a single, massive protostar, sometimes hundreds of times the mass of our Sun. This was a defining feature of population 3 stars, those formed from primordial gas. They were likely extremely massive, short-lived, and violent in their death throes. But before their cataclysmic demise, they altered the nature of the gas clouds from which they formed. Their intense ultraviolet radiation ionized nearby gas, breaking apart molecular hydrogen and heating the surrounding medium. Their powerful winds and eventual supernovae enriched the interstellar medium with metals for the first time in cosmic history. And in doing so, they ended the era of the primordial gas cloud. Yet this ending was also a beginning. Once a primordial cloud gave birth to a population 3 star and was enriched with heavy elements, it became chemically distinct. It entered a new phase of cosmic evolution where metals enabled vastly more efficient cooling, allowing clouds to fragment into smaller stars, which had longer lifespans and greater stability. This chemical transformation was the first irreversible change in the cosmos. From that moment on, the pristine conditions that allowed for the first stars ceased to exist. The clock could not be turned back. The primordial era was over, and what followed was the galaxy-building epoch. Despite this, some primordial clouds may have remained unaffected by this chain reaction. Perhaps they drifted into voids, vast, underdense regions between the filaments of the cosmic web, escaping the reach of the first stars. Others may have been too low in mass to collapse, too isolated to encounter the ionizing radiation or mechanical feedback necessary to alter their structure. These are the clouds we seek today, those that never made the transition, that are still unlit archives of cosmic birth. To find one would be like finding an untouched patch of Earth from the Hadean Aeon, before the crust had fully formed or life had begun. It would be a glimpse of the world before the world, of the universe before the universe we know. And yet they are elusive. The universe is vast, and our instruments, though powerful, are constrained. Most of what we know about these clouds comes from simulations, grand computational reconstructions of the early universe that track how gas and dark matter evolved together. These simulations are the cosmic equivalent of time machines. They allow us to rewind the clock and watch as the first structures formed from chaos. And again, they show us the importance of small-scale behavior. Tiny fluctuations in density, infinitesimal changes in cooling rates, minute differences in ionization, these determined whether a cloud collapsed or remained dormant. The fate of a primordial gas cloud is a lesson in the butterfly effect on a cosmic scale. These simulations also tell us something that is both humbling and awe-inspiring. The vast majority of gas in the early universe never became part of a galaxy. Even today, most of the baryonic matter in the cosmos, hydrogen and helium from the Big Bang, is still located in intergalactic space. It remains in the form of diffuse clouds, often at temperatures of millions of degrees, forming the warm hot intergalactic medium, WIM. But some of it may still exist as cold, neutral hydrogen, perhaps even in primordial form. And because of this, we are not just looking back in time when we study these clouds. We are looking into the very scaffolding of the cosmos. If the galaxies are the ornaments on the cosmic tree, then the gas clouds are its branches. They connect everything, fuel everything, and yet remain largely invisible. Without them, galaxies would have nothing to form from and nothing to grow with. Stars would have no material to burn. Black holes would have nothing to devour. The very energy balance of the universe, the interplay between cooling, heating, expansion, and collapse, would be undone. In a very real sense, primordial gas clouds are the pulse of cosmic evolution. Slow, steady, and rhythmic, their collapse and dispersal over billions of years has shaped everything we can observe. But there is still one more avenue through which they may impact our understanding: cosmic inflation and the nature of the early quantum vacuum. Inflation theory suggests that the universe expanded exponentially fast in a fraction of a second after the Big Bang. This rapid expansion smoothed out any curvature and seeded the cosmos with quantum fluctuations that would later become galaxies, clusters, and filaments. The patterns of primordial gas cloud distribution, if we could map them in enough detail, might allow us to test the initial conditions set by inflation. Did these fluctuations follow a Gaussian distribution, as standard inflation predicts? Or are there subtle asymmetries, preferred directions, or non-random patterns that hint at something more exotic? If so, these clouds, still drifting after all these billions of years, might hold evidence of physics that occurred at energy scales far beyond what we can test in particle accelerators. They might contain the fossilized imprint of a quantum field that existed before time as we know it began. And this would make them not just cosmic relics, but keys to the deepest questions we can ask. Why is the universe structured the way it is? Why does it contain matter and not antimatter? Is our universe part of a multiverse? What laws govern the first trillionth of a second after the Big Bang? To answer these questions, we will need not just better telescopes or more detailed simulations. We will need to listen differently, to observe the cosmos not just with instruments, but with new ways of thinking. We will need to find silence in the noise, and stillness in the motion. Because somewhere out there, between the galaxies and beyond the light, float the ancient clouds that remember when the universe was only a breath old. And within them, silent, cold, and waiting, might lie the answer to everything. These ancient, untouched primordial gas clouds, if they still exist, are perhaps the most delicate and profound time capsules in all of existence. Their story is not just about what they are made of, but what they represent. They are the bridge between the unknowable past and the visible universe. Everything we see now, superclusters, spiral galaxies, planetary systems, even the chemical ingredients of life itself, emerged because of what happened inside these clouds over 13 billion years ago. And yet, in all our modern understanding, in all our technological might, they remain among the least observed, least understood, and most enigmatic structures in the cosmos. But that mystery is what makes them so powerful. The very fact that these clouds are invisible in the traditional sense forces us to approach the universe differently. Instead of waiting for light to reach us from glowing stars, we have to detect the shadows, the gentle fingerprint these clouds leave on the light of more distant quasars. This is not intuitive. It's a kind of reverse astronomy. Where typical observations search for presence through emission, here we search for absence through absorption. When light from a quasar, traveling for billions of years, passes through a primordial gas cloud, certain wavelengths, especially those in the ultraviolet, like the Lyman alpha line, get absorbed. And that tells us where neutral hydrogen still floats. These patterns of absorption are faint, numerous, and beautifully complex. They form what we call the Lyman alpha forest, a dense field of spectral lines that, when decoded, becomes a map of invisible matter in the early universe. But what's breathtaking is that we can go even further than just locating these clouds. By analyzing how much light is absorbed, how it's shifted, and how it broadens, astronomers can estimate not only the density and temperature of the cloud but also its velocity, its size, and even how it is shaped by the surrounding gravitational field. In this way, we aren't just detecting clouds, we are listening to their dynamics, their movements, their history. Some clouds appear to be in the process of collapsing, others drifting within the gravitational pull of ancient dark matter halos, and some, perhaps the oldest, lie perfectly still, remnants of a time when the cosmos had just cooled enough for matter to exist in atomic form. And this ability to hear the cosmos whispering through the Lyman alpha forest gives rise to one of the most ambitious goals in cosmology: the reconstruction of the cosmic web. By collecting enough of these absorption patterns from quasars scattered across the sky, we can begin to rebuild the large-scale structure of the universe, not just what we see, but what lies between. The filaments, voids, nodes, and sheets of matter that form the scaffolding upon which galaxies hang all began with primordial clouds being pulled into place by dark matter. These reconstructions reveal that galaxies do not form randomly, but along the tendrils of invisible hydrogen that stretch across the cosmos. Every galaxy is a bloom on the branches of this web, and every branch was once a dense strand of primordial gas collapsing slowly into the first stars. It is poetic, then, to think of these clouds not just as clouds, but as cosmic cartographers, drawing the outlines of a universe that did not yet know what it would become. And their influence did not end with the birth of stars. The radiation from the first stars initiated a profound transformation in the intergalactic medium, a process known as cosmic reionization. As ultraviolet photons from the first population 3 stars and nascent galaxies flooded the universe, they began to break apart neutral hydrogen atoms. What followed was a slow and complex battle between darkness and light. Ionized bubbles expanded, overlapped, and eventually reionized most of the hydrogen in the universe. But in the shadows between these expanding spheres of radiation, neutral primordial gas clouds still survived. They were the last bastions of the ancient world, resisting the transformation of the cosmos by hiding in the deepest voids and most isolated pockets of space. And herein lies one of the great mysteries still unanswered. When exactly did reionization finish? How complete was it? Are there still fragments of untouched hydrogen drifting in the farthest reaches, beyond the reach of all known galaxies? These questions are not just historical curiosities. They impact our understanding of how galaxies form, how light travels, and how matter behaves in its most pristine state. Detecting a truly unionized gas cloud, one that has never been touched by starlight, would be one of the greatest discoveries in modern cosmology. It would be the closest thing to observing the universe before time, a fragment of reality, as it was before complexity arose. To pursue these questions, astronomers are building and planning some of the most ambitious instruments ever conceived. The James Webb Space Telescope, JWST, already peering into the earliest galaxies, is expected to push the detection limit deep into the heart of cosmic dawn. The Square Kilometer Array, SKA, will soon allow us to detect the faint 21 cm line of neutral hydrogen from the epoch of reionization, providing a 3D map of the cosmic web at a time when the first light was only just beginning to ripple through space. These instruments, alongside advanced simulations and AI-driven data analysis, are creating a new kind of astronomy, one where we don't just look at what is bright, but we infer what was hidden. And this brings us to one final, mind-bending idea. What if some of these primordial gas clouds did something utterly unexpected? What if they formed stars, but not the kind we know? What if conditions in some early clouds allowed for the birth of non-fusional objects, giant hydrogen spheres stabilized by exotic physics, such as dark matter interactions, scalar fields, or modified gravity? Could these be dark stars, hypothetical objects powered not by fusion but by dark matter annihilation in their cores? If even a few of these existed, they would have completely different lifespans, temperatures, and evolutionary paths. They might emit faint infrared signals, or none at all. They might be the ancestors of supermassive black holes we see at high redshift, those impossibly large black holes that seem to have formed too early to fit conventional models. Perhaps some primordial gas clouds collapse directly, skipping the star phase entirely, to form these behemoths in a process called direct collapse black hole formation. This idea shakes the very roots of how we understand cosmic structure formation. Because if such paths exist, then primordial gas clouds were not just precursors to stars and galaxies. They were the potential progenitors of every possible cosmic object, including those we cannot yet detect. Every primordial cloud, then, becomes a question mark, a gamble the universe made before any rules were firmly in place. Some rolled into stars. Others dispersed. Some stayed dormant. And some, perhaps, evolved into something beyond our imagination. We do not know all their stories. We may never find them all. But they are out there, silent witnesses to creation, drifting still, harboring secrets in their cold, ancient hearts. And when we look at the sky through telescopes that pierce billions of years into the past, we are not just seeing stars. We are seeing the flickering shadows cast by clouds long gone. And if we listen closely enough, through the noise, through the starlight, through the data, they may yet whisper back. As we dive deeper into the enigma of primordial gas clouds, we begin to understand that their relevance extends far beyond their historical role in star formation. They are not merely the before, in a linear sequence of cosmic evolution. They are ongoing participants, subtle, diffuse, yet essential, in the grand narrative of how the universe behaves. Even in our modern era, billions of years after the Big Bang, these clouds have not faded into irrelevance. They continue to influence the thermodynamics of the intergalactic medium, fuel galaxies with new material, and offer rare windows into a cosmos that still holds more questions than answers. Take, for example, the infall of cold gas into galaxies, a process we once thought was relatively straightforward. We imagine that gas fell into galaxies, cooled down, and eventually became part of stars. But recent simulations and observational evidence suggest that much of the gas feeding galaxies arrives not as warm or ionized matter but as cold, dense streams, often originating from intergalactic filaments. These streams may be direct descendants of primordial gas clouds, unchanged in composition, still nearly metal-free, and guided into gravitational wells by the architecture of dark matter halos. When they reach a galaxy, they provide not just mass but fuel for starbursts, driving sudden and explosive periods of star formation. These cold flows are not relics, they are rivers still running today, transporting the untouched past into the living present. And yet, the role of these clouds is not always constructive. In some cases, they become barriers to formation and change. In regions where the clouds are too diffuse or never reach sufficient density, they prevent the gravitational collapse needed for star formation. These become what astronomers call dark galaxies or failed galaxies, structures rich in hydrogen but devoid of stars. These systems are nearly invisible to optical telescopes, detectable only through their gravitational effects or, in rare cases, via faint 21 cm radio signals. If we could observe more of these dark galaxies, we would gain invaluable insight into why some primordial clouds succeeded in birthing galaxies and others did not. The cosmic lottery of initial conditions, dark matter concentration, and environmental isolation determined which clouds would become the nurseries of light, and which would remain silent voids. But perhaps the most haunting mystery of all lies in what we still can't detect. Despite our growing arsenal of instruments, there is a vast amount of missing baryonic matter in the universe, ordinary matter that should be there according to our models and calculations, but has never been directly observed. Many scientists believe that this matter exists in the form of diffuse, ionized gas spread thinly between galaxies, possibly connected to the same primordial gas structures that formed after the Big Bang. If this is true, then primordial clouds are not just historical footnotes. They are active repositories of the cosmos' hidden mass, linking observable structures to the elusive remainder of the universe's matter budget. Consider the role of magnetic fields in all this, a factor long ignored in early models of primordial gas evolution. Modern simulations suggest that even extremely weak primordial magnetic fields could have had significant effects on how these clouds fragmented, how they collapsed, and how efficiently they could cool. A magnetic field alters pressure, guides charged particles, and influences turbulence. In a universe where molecular hydrogen cooling was already tenuous, even a slight modification in turbulence or temperature distribution could mean the difference between star formation and eternal silence. If primordial gas clouds were magnetized, even slightly, then their evolution was even more complex and variable than we've ever imagined. There's another factor too, one far more alien, speculative, and chilling: interaction with dark matter substructures. Dark matter is not smooth. It forms clumps, subhalos, and filaments. As primordial gas clouds drifted through the early universe, they were caught in the gravitational embrace of these substructures. In many cases, this was beneficial. It provided the gravitational scaffolding needed for collapse. But in others, it may have disrupted the clouds, stretched them thin, or even flung them into voids. What this means is that some of the most ancient gas clouds might have been torn apart before they could ever evolve, their material lost to intergalactic space, unstructured and forgotten. Yet traces of their disrupted past may still be detectable, in the form of low-density hydrogen clouds seen in absorption, drifting without form or destiny. And still, we must ask, could any of these clouds have survived unchanged to this day? It's not impossible. Deep in the cosmic voids, regions where galaxy density is extremely low, there could still be mini halos of pristine hydrogen, never touched by star formation or heavy element contamination. Detecting them would be like finding amber-encased DNA from the dawn of time. They would not just inform us about cosmic history, they would become experimental probes into fundamental physics. These clouds could help us constrain the properties of dark matter, such as whether it is warm or cold, determine the exact timeline of reionization, and even reveal variations in fundamental constants like the fine structure constant or electron-to-proton mass ratio over cosmic time. Indeed, some theorists believe that variations in absorption line measurements across different clouds at different distances might hint at such variations, suggesting that the laws of physics themselves may have evolved subtly across time and space. This is a bold claim, and one that remains controversial. But it is telling that the data used to support or refute such a profound idea comes from none other than the spectral signatures of primordial gas. These clouds are not just a side story in cosmology. They are the canvas upon which the universe's first truths were painted. And now, with each year, we are peeling back more of that canvas. Observatories like the Atacama Large Millimeter/Submillimeter Array, ALMA, the European Extremely Large Telescope, ELT, and the Nancy Grace Roman Space Telescope will push the frontier of observation ever closer to the edge of time. They may reveal more about these clouds than we ever thought possible, perhaps even allowing us to detect the first flows of gas into forming galaxies, or to directly measure the temperatures, densities, and motion of clouds less than 1 billion years old. But what makes primordial gas clouds so extraordinary is not merely their scientific utility. It is their poetic place in the cosmic narrative. They are the unformed clay of existence, the blank page of the universe's first draft, the breath before the first word. And though their story is subtle, quiet, and hidden, it is the story that all other stories depend upon. We may never observe them all. We may never know each cloud's fate. But in chasing them, in studying them, in listening to their spectral echoes across billions of years, we are doing more than astronomy. We are reaching into the very origin of form, of structure, of light, and asking the question, how did the void begin to dream? And as we continue to chase that dream, the one birthed in the heart of darkness, before the first star flared into existence, we come face to face with the stark, humbling reality that our entire cosmic identity is rooted in the silent, formless cradles we call primordial gas clouds. Every atom in your body, every molecule in the oceans, every spark in the fires of our civilization, once drifted anonymously in a vast cloud of neutral hydrogen, unshaped and unremarkable. These clouds were not designed for us. They were not aware of what they carried. But they were the primordial reservoirs of potential, and they held within them the seeds of all creation. And that makes their mystery all the more haunting. Because these clouds did not evolve with consciousness, or design, or will. They were sculpted by the cold forces of physics, gravity, thermodynamics, quantum uncertainty, into vast, delicate forms that hung in the infant universe like vapor trails across a blank sky. Some collapsed, igniting into starlight. Others faded, evaporated, or were destroyed by radiation and violence. And some, just some, may have escaped it all. Survived untouched. Holding in their chemistry the pristine signature of a universe before it changed, before it became complex, before it even glimmered with light. This is why astronomers across the world spend years examining the faintest patterns in the light from distant quasars. Why they build massive telescopes on desolate mountain peaks and bury detectors in frozen deserts. They are not just chasing stars. They are chasing silence. They are searching for the unburned truth that existed before galaxies shouted into the void. Every absorption line, every shift in frequency, every missing photon is a message. And sometimes it is from a cloud that has never been seen, never glowed, and never been altered by anything since the Big Bang itself. But we also know that these clouds, though ancient, are not immune to evolution. As galaxies grow, they produce stellar winds, radiation pressure, and outflows of hot gas that stretch for hundreds of thousands of light years. These powerful forces collide with the surrounding intergalactic medium, pushing, heating, and sometimes mixing with any nearby primordial gas. In this way, even the purest clouds can be polluted by cosmic feedback, changing their composition in subtle but profound ways. Tracing the chemical fingerprints of gas clouds helps us not only study their origin but understand how far the influence of galaxies extends, and how violently the cosmic ecosystem interacts. In fact, one of the most exciting developments in recent years has been the detection of pristine gas clouds near galaxies, but not within them. These clouds are tantalizingly close enough to be affected by the gravity of galaxies, but far enough that they've never been enriched with heavy elements. These rare detections suggest that primordial gas can linger around galactic halos for billions of years, never fully collapsing, never fully dispersing. They are ghostly companions to the brilliant cities of stars we admire in space photos. They are the quiet outskirts of the universe's consciousness, where memory of the beginning still survives. And as we search for these clouds, we also confront the limits of our tools. Traditional spectroscopy, even with the power of modern telescopes, requires bright background sources, quasars, gamma-ray bursts, or active galaxies, to backlight the clouds and reveal their absorption patterns. But these background lights are rare, and they're scattered across the sky like lonely beacons. That means vast regions of the universe remain unprobed, hidden in observational darkness. To map these primordial structures more fully, we'll need a revolution in detection. Perhaps 21 cm tomography will finally offer us a way to chart neutral hydrogen directly, without needing backlights. Perhaps one day, gravitational lensing will allow us to magnify distant faint sources just enough to make the invisible visible. Or perhaps quantum technologies will uncover new windows into how intergalactic gas behaves at extreme distances. All of this points to one overwhelming truth: we are still at the beginning of understanding the beginning. Every new observation is a first draft. Every cloud we detect is just one thread in a vast tapestry we've only started to unravel. And that tapestry stretches across more than just space. It crosses the deepest philosophical boundaries of what we consider knowable. Because in seeking out these clouds, we aren't just asking what is out there. We are also asking, why is there something rather than nothing? Why did this material condense? Why did it ignite? And why did it give rise to life, awareness, and meaning? That may sound metaphysical. But it is not. It is science in its purest form, curiosity without end, fueled by structures without name, guided by signals without shape. Even now, as cosmologists simulate the birth of the universe on supercomputers, they begin with equations that attempt to model how these primordial clouds would behave under different conditions: varying dark matter densities, changes in the strength of cosmic inflation, fluctuations in baryon acoustic oscillations. Every simulation of a galaxy must first begin with the story of gas: how it fell, how it cooled, how it clumped, and how it either sparked or didn't. Without understanding primordial gas clouds, we are guessing at the foundation of the very structures we seek to understand. They are the load-bearing beams of the cosmic cathedral, and yet we still don't know how many were ever laid. And the mystery deepens when we consider the role of cosmic voids. These immense, underdense regions of the universe, many millions of light-years wide, may harbor vast quantities of neutral hydrogen that never formed stars or galaxies. These might be the true repositories of untouched primordial clouds, sheltered from radiation, metal enrichment, and galactic feedback for billions of years. Detecting them requires sensitivity far beyond our current limits. But if we ever manage it, we might find that some parts of the universe have never changed since the moment of recombination, the moment the universe first became transparent. That thought alone is staggering. It suggests that time has not touched everything, and that the Big Bang still echoes in forms far more literal than we imagined. In these untouched clouds, we might even find the fossils of failed universes, regions where symmetry breaking never occurred, or where matter cooled too quickly, or where the initial density fluctuations were too slight to allow collapse. They may be the great counterfactuals of cosmology, what the universe could have been had its early parameters varied just a little. In these regions, the very nature of matter, light, and structure could be subtly different, not in ways that violate physics, but in ways that reveal how fragile our cosmic history truly is. So as we look forward, toward deeper surveys, better detectors, and more precise simulations, we must not forget the philosophical weight of what we are studying. Primordial gas clouds are not just part of our past. They are keys to a deeper understanding of existence itself. They are the first page of the universe's autobiography, written not in ink, but in the quiet drift of hydrogen atoms, shaped by forces more ancient than starlight, and preserved in the shadows cast by galaxies we may never see. And so we search. Not for answers written in fire, but for whispers left in darkness. Because somewhere, drifting still through the vast halls of the cosmos, untouched and unseen, the first breath of the universe waits to be heard. The pursuit of primordial gas clouds pushes us to the very edge of observational astronomy and theoretical physics, forcing us to confront the limits of both technology and imagination. When we attempt to detect these clouds, we are essentially trying to see the universe as it was more than 13 billion years ago, at a time when the cosmic landscape was far simpler, yet more mysterious. It is a time before galaxies had fully formed, before stars ignited nuclear furnaces, before heavy elements existed to paint the universe in a rich tapestry of colors. Instead, the cosmos was dominated by vast, diffuse clouds of hydrogen and helium, simple in composition but complex in behavior. One of the main tools scientists use to study primordial gas clouds is the 21-centimeter hydrogen line, an emission or absorption signature created when the electron in a hydrogen atom flips its spin relative to the proton. This faint radio wave allows astronomers to map neutral hydrogen gas across vast distances. However, detecting the 21-centimeter signal from the earliest epochs is extraordinarily difficult because the universe's expansion redshifts this signal to longer wavelengths, and because the signal itself is incredibly weak compared to the foreground noise from our own galaxy and human-made radio interference. Still, projects like the Hydrogen Epoch of Reionization Array, HERA, and the Square Kilometer Array, SKA, are designed specifically to overcome these challenges, aiming to create three-dimensional maps of hydrogen from the cosmic dawn. If successful, they will revolutionize our understanding of how primordial gas clouds transitioned into the first luminous objects. But hydrogen is just the beginning. To truly understand primordial gas clouds, we must delve into their chemical evolution and physical state. In the early universe, these clouds were almost entirely metal-free, containing only the lightest elements formed during Big Bang nucleosynthesis. Without heavier elements like carbon, oxygen, or iron to act as efficient coolants, gas clouds face significant hurdles in cooling and collapsing under gravity. Instead, molecular hydrogen, H2, which forms via rare interactions in the early gas, was the primary coolant. This made the conditions for star formation vastly different than in modern clouds enriched by metals. Simulations show that the first stars, the so-called population 3 stars, were likely much more massive than today's stars, sometimes hundreds of times the mass of the Sun. These stars burned hotter and lived shorter lives, producing the first heavy elements through their explosive deaths, thereby enriching their surroundings and altering the chemistry of future gas clouds. Understanding this transformation, from simple primordial clouds to complex, metal-enriched star-forming regions, is critical. It holds the key to knowing how the first galaxies formed and evolved. Observing these processes directly is near impossible because the objects involved are incredibly distant and faint. Yet, by studying the absorption lines imprinted on the light of distant quasars, active galactic nuclei shining across billions of light-years, astronomers have pieced together a picture of how primordial gas clouds evolve chemically and physically over time. Another remarkable phenomenon linked to primordial gas clouds is their interaction with cosmic reionization, a pivotal era in cosmic history when the first stars and galaxies emitted enough energetic radiation to ionize the neutral hydrogen permeating the universe. Reionization transformed the universe from a cold, dark fog to a transparent cosmos filled with light. The role of primordial gas clouds here is twofold. On the one hand, they were the raw material for star formation. On the other hand, their ionization state influenced how quickly reionization proceeded. Large, dense clouds could shield themselves and their surroundings from ionizing photons, delaying reionization locally. Conversely, more diffuse clouds allowed radiation to propagate, accelerating the process. The patchwork nature of reionization, revealed through observations of the cosmic microwave background and high redshift galaxies, reflects the complex interplay between primordial gas clouds, star formation, and radiation. Moreover, primordial gas clouds are believed to be involved in the formation of the universe's earliest supermassive black holes. How these colossal objects, some billions of times the mass of our Sun, formed so quickly after the Big Bang is one of the most pressing puzzles in astrophysics. One leading hypothesis suggests that direct collapse black holes formed when massive primordial gas clouds collapsed rapidly, bypassing normal star formation and instead creating dense, massive objects that rapidly became black holes. These primordial clouds had to avoid fragmenting into smaller clumps, a feat thought possible under specific conditions such as intense ultraviolet radiation suppressing molecular hydrogen formation, allowing the cloud to stay hot and collapse directly. If true, these clouds represent a critical link in the cosmic chain leading to the supermassive black holes that anchor galaxies, including our Milky Way. The more we explore, the more we realize that primordial gas clouds are not static relics frozen in time but dynamic participants in cosmic evolution. Their shapes, densities, temperatures, and chemical compositions vary wildly, influenced by local radiation fields, shock waves from early supernovae, and the gravitational pull of dark matter. These clouds can form filamentary structures stretching over millions of light years, echoing the cosmic web's large-scale pattern. Their motions and interactions affect how matter flows into galaxies and clusters, influencing star formation rates, galaxy morphology, and even the chemical enrichment of the intergalactic medium. Yet, despite the progress, many questions remain unresolved. How did the precise balance between cooling, heating, and gravitational collapse in primordial gas clouds determine the initial mass function of the first stars? Did primordial magnetic fields exist and influence the formation of these clouds? How did feedback from the first stars and black holes reshape the distribution and properties of the gas? Can we detect pristine clouds untouched by star formation today, hidden in cosmic voids or halos? The quest to answer these questions drives astronomers to build ever more powerful telescopes, develop sophisticated simulations, and collaborate across disciplines. In this endeavor, the study of primordial gas clouds stands as a bridge between the observable universe and the theoretical foundations of cosmology. It challenges us to understand matter at its most fundamental level, to trace the cosmic flow of energy and elements, and to glimpse the universe as it was before complexity took hold. Each new discovery is a step closer to decoding the origin story written in the language of hydrogen and helium, the elemental whispers that have echoed for nearly 14 billion years, waiting for us to listen. As we deepen our exploration of primordial gas clouds, the interplay between theory and observation becomes ever more critical. These clouds are not just static entities floating idly in the cosmic expanse. They are dynamic, evolving systems influenced by a delicate balance of competing forces: gravity pulling matter inward, thermal pressure pushing outward, radiation heating and ionizing, and magnetic fields twisting and shaping their structures. Theoretical models simulate these forces at an extraordinary level of detail, often requiring immense computational resources to capture the subtle processes governing the cloud's behavior on scales from subparsec clumps to megaparsec filaments. One particularly fascinating aspect is how primordial gas clouds serve as the nurseries for the universe's first stars, known as population 3 stars. These stars hold a unique place in cosmic history, representing the first time nuclear fusion ignited within matter that was nearly pristine, untouched by the metals forged in the hearts of previous stars. Their formation depended heavily on the cooling pathways available in the gas. Since metals and dust grains, which dominate cooling in modern molecular clouds, were absent, the clouds had to rely on inefficient coolants like molecular hydrogen, H2, and deuterium hydride, HD. These molecules, fragile and scarce, formed slowly and in limited quantities through gas phase reactions catalyzed by trace electrons. The inefficiency meant that primordial clouds remained hotter and more massive than modern star-forming clouds, favoring the formation of stars far more massive, some theorized to be over 100 solar masses. These massive population 3 stars lived fast and died young, ending their lives in cataclysmic supernovae or direct collapse into black holes. Their explosive deaths seeded the surrounding medium with the first heavy elements, enriching subsequent generations of gas clouds and enabling more efficient cooling and star formation. This cosmic chemical evolution, initiated within primordial gas clouds, set the stage for the complexity that followed: the formation of galaxies, planets, and eventually, life itself. Yet, despite advances, the direct detection of population 3 stars remains elusive. They are too distant and too short-lived to be observed with current telescopes, hidden behind layers of intervening gas and dust. Instead, astronomers search for indirect signatures, such as peculiar chemical abundance patterns in ancient stars in the Milky Way halo or unique spectral features in distant galaxies that might hint at primordial star formation. These signatures offer tantalizing clues but also highlight the uncertainties and the immense challenge of reconstructing cosmic history from such faint whispers. Primordial gas clouds also play a crucial role in the epoch of reionization, a transformative era when the first luminous sources ionized the neutral hydrogen that filled the universe after recombination. Before reionization, the universe was a dark, opaque fog where photons scattered off neutral hydrogen atoms. The birth of the first stars and galaxies emitted ultraviolet light energetic enough to ionize hydrogen, carving out expanding bubbles of ionized gas. Primordial gas clouds, as the raw material for star formation, directly influenced the timing and progression of this epoch. Denser clouds could self-shield, remaining neutral longer and delaying ionization locally, while more diffuse regions were ionized earlier. Mapping the distribution and properties of these clouds during reionization is critical to understanding how the universe transitioned from darkness to light. Modern observational campaigns utilize a variety of techniques to probe primordial gas clouds and their environments. Quasar absorption spectroscopy remains a cornerstone method, where light from distant quasars filters through intervening gas, imprinting absorption lines that reveal the chemical composition, density, temperature, and velocity of the clouds. These observations have identified numerous Lyman alpha forest lines, each corresponding to a gas cloud along the line of sight, painting a detailed picture of the intergalactic medium's structure. More recently, 21 cm cosmology aims to directly detect the neutral hydrogen signal from the epoch of reionization and even earlier. While challenging due to foreground contamination and signal weakness, success in this area promises a revolutionary three-dimensional view of primordial gas distribution over cosmic time. Beyond their role in star formation and reionization, primordial gas clouds may have contributed to the formation of supermassive black holes in the early universe. Observations of quasars at redshifts above 7 reveal black holes with masses exceeding 1 billion suns, which is difficult to explain given the limited time since the Big Bang. One hypothesis posits that massive primordial gas clouds, under specific conditions, such as intense radiation fields preventing molecular cooling, collapse directly into massive black hole seeds without fragmenting into stars. These direct collapse black holes could then rapidly grow by accretion and mergers to reach the supermassive scales observed. Understanding the properties of primordial gas clouds that allow such collapse is a frontier topic, blending astrophysics, cosmology, and high-energy physics. The study of primordial gas clouds also connects to the elusive nature of dark matter. Since these clouds formed in gravitational potential wells created by dark matter halos, their distribution and evolution carry indirect information about the dark matter's properties. Comparing observed structures to predictions from dark matter models helps constrain the nature of this mysterious substance, which constitutes about 85% of the universe's matter content. In some models, interactions between baryonic gas and dark matter particles could influence gas cooling and cloud collapse, affecting the timeline and characteristics of primordial star formation. Moreover, primordial gas clouds are not isolated, they interact with their environment. Stellar feedback from the first stars, including intense ultraviolet radiation, stellar winds, and supernova explosions, dramatically reshape their surroundings. This feedback can both trigger and suppress star formation in neighboring clouds, driving a complex cycle of cosmic evolution. The interplay between gas cooling, collapse, and feedback creates a patchwork of ionized and neutral regions, dense knots and diffuse voids, across the early universe, setting the stage for the rich diversity of cosmic structures we observe today. Despite these insights, many mysteries remain. How homogeneous were primordial gas clouds across the universe? Did they form universally similar structures, or did variations in local conditions produce diverse outcomes? Can we identify truly pristine clouds that have remained chemically unpolluted since the Big Bang? Are there pockets of the universe where primordial gas still exists in isolation, and can we observe them directly? What role did magnetic fields play in shaping these clouds, if any? Addressing these questions requires pushing the boundaries of observation and theory. In the coming decades, the deployment of next-generation telescopes such as the James Webb Space Telescope, JWST, the Extremely Large Telescope, ELT, and the Square Kilometer Array, SKA, promises to open unprecedented windows into the early universe. These instruments will probe deeper, with higher sensitivity and resolution, allowing us to detect the faint glow of primordial galaxies, measure the 21 cm hydrogen signal across cosmic time, and map the distribution of gas with exquisite detail. Together with advances in computational astrophysics, these observations will transform our understanding of primordial gas clouds from theoretical constructs into well-characterized cosmic phenomena. The exploration of primordial gas clouds is more than an academic pursuit. It is a quest to trace our cosmic origins back to their purest form. These clouds, vast and silent, hold the blueprint for everything that followed: the stars, planets, galaxies, and life. By studying them, we confront the profound question of how order and complexity arose from a nearly uniform, featureless beginning. The whispers of hydrogen atoms echo through billions of years, inviting us to listen, to learn, and to marvel at the universe's enduring mystery. Peering even further into the nature of primordial gas clouds, we encounter the remarkable complexity hidden within what might initially seem like simple accumulations of hydrogen and helium. While these clouds primarily consist of the two lightest elements, their internal physical conditions are anything but trivial. Their densities, temperatures, and turbulence levels vary widely, influenced by gravitational forces, radiation fields, and the faint but crucial traces of molecular chemistry. Even in the absence of metals, the formation of molecular hydrogen and trace molecules like HD, deuterium hydride, provides critical cooling pathways that determine whether a cloud can collapse to form stars or remain diffuse. One of the fundamental questions about these clouds involves their fragmentation properties. In modern molecular clouds enriched with metals and dust, cooling is efficient enough that large clouds fragment into many small clumps, leading to the formation of stars of varied masses. But in primordial clouds, the limited cooling capacity means that fragmentation is suppressed, favoring the formation of massive stellar cores. This difference profoundly impacts the initial mass function of stars formed in the early universe and, consequently, the evolution of early galaxies and the chemical enrichment history of the cosmos. Simulating this fragmentation and collapse requires solving complex coupled equations of hydrodynamics, chemistry, radiative transfer, and gravity, often across many scales from subarastronomical unit sizes, the size of solar systems, up to kiloparsecs, thousands of light-years. Modern numerical simulations use adaptive mesh refinement and smooth particle hydrodynamics to capture these scales dynamically. Results from such simulations have revealed that primordial gas clouds likely formed in dark matter halos with masses around 1,000,000 times that of the Sun, deep enough potential wells to hold gas against pressure forces but still susceptible to feedback effects from emerging stars. Another fascinating area of study is the influence of primordial magnetic fields on gas cloud evolution. While magnetic fields are ubiquitous in modern galaxies, their origin is not fully understood, and it remains an open question whether seed magnetic fields existed in the early universe before structure formation. If present, even very weak magnetic fields could alter the dynamics of gas collapse by providing additional pressure support, affecting angular momentum transport, and possibly influencing the fragmentation scale. Some theories propose that tiny magnetic fields could be generated through processes like the Biermann battery effect during the formation of the first structures, subsequently amplified by turbulent dynamos. The presence or absence of magnetic fields in primordial gas clouds has significant implications for the morphology and spin of the first stars and black holes. The role of radiative feedback from the first luminous sources on primordial gas clouds cannot be overstated. As the first massive stars ignited, their intense ultraviolet radiation began to ionize and heat surrounding gas, creating expanding ionized bubbles known as H2 regions. This radiation could both trigger and inhibit further star formation. It could compress neighboring gas, inducing collapse, or it could heat and disperse gas, preventing collapse. Similarly, supernova explosions injected energy and metals into the environment, driving shocks through the primordial gas and stirring turbulence. These processes created a highly inhomogeneous environment, where pockets of neutral, ionized, metal-enriched, and metal-poor gas coexisted and evolved in complex feedback loops. Studying these feedback effects is crucial for understanding the timeline and topology of cosmic reionization. Observations suggest that reionization was neither instantaneous nor uniform but patchy and extended over hundreds of millions of years. Primordial gas clouds, by virtue of their distribution and density, influenced the size and growth of ionized bubbles. Denser clouds shielded regions from ionizing photons, creating neutral islands within ionized volumes, while low-density regions were reionized earlier. Mapping these structures through 21 cm line tomography and other observations is a major goal of current and future radio astronomy projects. A lesser-known but intriguing possibility is that primordial gas clouds could still exist today, relatively untouched by star formation and chemical enrichment. These hypothetical clouds would be relics of the early universe, residing in the outskirts of galaxies or in cosmic voids. Detecting them is challenging due to their faint emission and absorption signatures, but their discovery would provide a unique laboratory for studying conditions akin to those shortly after the Big Bang. Some candidate objects, such as certain high-velocity clouds in the Milky Way halo or extremely metal-poor damped Lyman alpha systems, might represent such primordial reservoirs. Confirming their primordial nature requires precise measurements of their chemical abundances, kinematics, and environments. Furthermore, primordial gas clouds have been implicated in the formation of exotic astrophysical phenomena, such as supermassive stars and direct collapsed black holes. Under specific conditions, such as intense ultraviolet radiation suppressing molecular hydrogen cooling, massive gas clouds could avoid fragmentation and collapse directly into enormous stars or black hole seeds. These processes might explain how supermassive black holes, observed as quasars at very high redshifts, formed so rapidly in the young universe, challenging traditional growth models. Understanding these pathways requires detailed knowledge of the thermal and chemical state of primordial gas clouds, as well as the radiation backgrounds present during the cosmic dawn. The study of primordial gas clouds also intersects with cosmological parameters and fundamental physics. For instance, variations in the cosmic microwave background radiation or in the primordial power spectrum of density fluctuations could influence the formation and distribution of these clouds. Similarly, theories involving exotic dark matter interactions or alternative cosmologies might leave imprints on the gas cloud's characteristics, offering indirect tests of fundamental physics through astrophysical observations. As technology advances, so do our methods to probe these elusive structures. The launch of the James Webb Space Telescope has already begun to push the observational frontier closer to the epoch of reionization, detecting galaxies and star-forming regions in the first few 100 million years after the Big Bang. Ground-based telescopes equipped with sensitive spectrographs target absorption features from gas clouds and quasar spectra, while massive radio arrays aim to detect the faint 21 cm signal of neutral hydrogen. In tandem, numerical simulations grow ever more sophisticated, incorporating a wealth of physics to model the interplay between dark matter, gas dynamics, chemistry, and radiation. Primordial gas clouds stand as both the literal and metaphorical foundation of the cosmic story. They are the reservoirs from which the first stars ignited, the canvases upon which the universe painted its earliest masterpieces of light and structure. Despite their apparent simplicity, these clouds embody some of the most profound mysteries of modern astrophysics, how matter organizes itself under gravity, how the first light transformed darkness, and how the universe's complexity emerged from near uniformity. To unravel these mysteries, humanity must continue its pursuit with ever greater curiosity, ingenuity, and determination, peering across billions of years and trillions of miles to catch the faint signals of the universe's infancy. Delving even deeper into the enigma of primordial gas clouds reveals their intrinsic connection to the large-scale structure of the universe, the cosmic web, a vast network of filaments, sheets, and voids composed of dark matter and baryonic gas. These gas clouds did not form in isolation. Rather, they are intricately woven into this cosmic tapestry. Dark matter halos provide the gravitational scaffolding where baryonic matter, primarily hydrogen and helium gas, accumulates and cools. The density fluctuations seeded during inflation, minute variations in the early universe's density field, grew over time through gravitational instability, leading to the hierarchical assembly of structures. Primordial gas clouds are therefore the natural condensations within these evolving halos, marking the first steps from a smooth early universe to the intricate cosmic web we observe today. The density, temperature, and chemical composition of these primordial clouds are not uniform but vary systematically with their location in the cosmic web. In denser filaments, gas tends to be compressed and shock-heated as it falls into the gravitational wells, often reaching temperatures that allow atomic cooling to proceed efficiently. This process facilitates the formation of the first luminous objects. Conversely, gas in less dense voids remains cooler and more diffuse, possibly preserving pristine conditions for longer periods. The interaction between these environments influences star formation efficiency, feedback effects, and ultimately the growth of galaxies. An essential tool in exploring the large-scale distribution of primordial gas clouds is the Lyman alpha forest, a series of absorption features in the spectra of distant quasars. Each absorption line corresponds to a cloud of neutral hydrogen along the line of sight, enabling astronomers to map the intergalactic medium structure over vast cosmic distances. The fine details of these absorption lines, such as their width, depth, and spacing, inform us about the temperature, density, and velocity dispersion of the primordial gas clouds. Statistical studies of the Lyman alpha forest have confirmed that the intergalactic medium is highly structured and trace the evolution of cosmic density fluctuations, providing critical constraints on cosmological models. Moreover, the primordial gas clouds serve as the battlefield for competing physical processes shaping the early universe's thermal history. The balance between gravitational collapse and various feedback mechanisms, such as photoheating by ultraviolet backgrounds, shock heating from structure formation, and cooling via atomic and molecular transitions, determines the cloud's fate. This interplay governs whether a cloud can collapse to form stars, remain in a quasi-stable state, or be dispersed back into the intergalactic medium. Understanding these processes requires integrating insights from atomic physics, fluid dynamics, radiation transfer, and cosmology, making the study of primordial gas clouds a true multidisciplinary endeavor. One of the most profound mysteries involving primordial gas clouds concerns their role in cosmic chemical evolution. The first stars forged the initial heavy elements, but how these metals dispersed into the surrounding gas and mixed to form later generations of stars remains an active research area. Metals alter the cooling efficiency of gas clouds dramatically, enabling fragmentation into smaller masses and thus the formation of low-mass, long-lived stars. Tracing the metal enrichment history through absorption lines and stellar archaeology provides clues about the timing, efficiency, and scale of early star formation and feedback. Beyond metals, primordial gas clouds may also harbor signatures of more exotic processes. For instance, they might be sensitive to non-standard particle physics phenomena, such as annihilating or decaying dark matter particles injecting energy into the gas, modifying its temperature and ionization state. Similarly, early cosmic rays generated by the first supernovae or black hole accretion could catalyze molecular formation or heat the gas, affecting star formation pathways. Detecting such subtle influences would open a window into physics beyond the standard model through astrophysical observations. The possibility that primordial gas clouds could influence cosmic microwave background (CMB) anisotropies is another intriguing avenue. While the CMB primarily reflects conditions at the surface of last scattering about 380,000 years after the Big Bang, the subsequent formation and evolution of gas clouds imprints secondary anisotropies via mechanisms such as the kinetic Sunyaev-Zeldovich effect and the Ostreicher-Vishniak effect. These subtle imprints carry information about the distribution and motion of ionized gas, thus connecting primordial clouds to observable signals in the microwave sky. Upcoming CMB experiments with higher sensitivity and resolution aim to exploit these effects to refine our understanding of structure formation and reionization. Technological advancements promise to revolutionize our observational capabilities. The James Webb Space Telescope has already begun to push the boundaries by identifying galaxies at redshifts greater than 10, offering glimpses of star formation when the universe was less than 500 million years old. Ground-based extremely large telescopes, with mirror diameters exceeding 30 meters, will allow detailed spectroscopic analysis of faint objects, probing the chemical and physical state of primordial gas clouds. Meanwhile, radio observatories such as the Square Kilometre Array will seek the faint 21 cm hydrogen emission and absorption signals from the cosmic dawn and epoch of reionization, mapping the neutral gas distribution in unprecedented detail. The scientific pursuit of primordial gas clouds is not only about cataloging cosmic relics but also about understanding the fundamental processes that govern the universe's transition from simplicity to complexity. These clouds embody the initial conditions for galaxy formation, star formation, and chemical enrichment, the building blocks for planets, life, and consciousness. By unraveling their mysteries, we touch upon the origin story of everything we know. Primordial gas clouds represent one of the most fascinating frontiers in astrophysics and cosmology. They are cosmic laboratories where physics at its most fundamental intersects with the grandest scales imaginable. Their study demands a blend of theory, observation, and computation, all driven by humanity's insatiable curiosity to understand our place in the universe. As new instruments come online and simulations grow ever more detailed, we stand on the cusp of profound discoveries that will illuminate these ancient clouds and, through them, the dawn of cosmic history itself. The narrative of primordial gas clouds also intertwines with the quest to understand the earliest phases of galaxy formation. These clouds, dense pockets of hydrogen and helium, collected within dark matter halos, formed the raw material from which the first galaxies arose. The gravitational attraction of dark matter concentrated these clouds, allowing them to cool and condense. Yet, the process was far from straightforward. The absence of heavy elements, which in modern galaxies act as efficient coolants through line emissions and dust interactions, meant that the primordial gas clouds had limited ways to lose heat and contract. This inefficiency influenced the size and structure of the first galaxies. Instead of forming compact, well-defined galaxies like those seen today, the earliest galaxies were likely diffuse and irregular, composed of massive clumps of primordial gas and massive stars. These proto-galaxies were dynamic, turbulent environments where intense ultraviolet radiation from the first stars altered the state of surrounding gas clouds. This radiation could ionize and heat the gas, creating pressure that pushed back against gravitational collapse, and in some cases, prevented further star formation for tens of millions of years. Moreover, the interactions between these primordial gas clouds and the dark matter halos were not static. As halos merged and grew through cosmic time, the gas clouds within them were compressed, shocked, and sometimes expelled, shaping the hierarchical growth of galaxies. The interplay between inflowing cold gas streams and outflowing winds from star formation and black hole activity created complex feedback loops. These feedback processes regulated star formation, influenced chemical enrichment, and affected the distribution and morphology of gas clouds within galaxies. A particularly compelling mystery is the nature of the first supermassive black holes and their relation to primordial gas clouds. Observations of quasars at very high redshifts, less than 1 billion years after the Big Bang, show black holes with masses of 1 billion solar masses or more. The rapid formation of such enormous black holes challenges standard models of black hole growth, which assumes slower accretion rates. One proposed solution involves the direct collapse of massive primordial gas clouds into black hole seeds of intermediate mass, bypassing the formation of a normal star. In this scenario, the gas cloud remains hot and avoids fragmentation due to intense radiation fields suppressing molecular hydrogen cooling, collapsing almost monolithically. Such direct collapse black holes, if they exist, provide a crucial link in understanding how supermassive black holes grew so quickly in the early universe. The specific environmental conditions needed for direct collapse, including gas inflow rates, metallicity thresholds, and radiation backgrounds, are still under intense study. Detecting these early black hole seeds directly is extremely challenging but would revolutionize our comprehension of early cosmic structure. Another facet of primordial gas clouds lies in their potential to reveal the nature of dark matter. While dark matter itself is invisible and non-interacting with electromagnetic radiation, its gravitational influence governs the formation and distribution of gas clouds. Certain alternative dark matter models, such as warm dark matter or self-interacting dark matter, predict different small-scale structures in the universe compared to the standard cold dark matter paradigm. These differences manifest in the abundance, size, and density profiles of dark matter halos, which in turn affect how primordial gas clouds form and evolve. For example, warm dark matter, consisting of lighter, faster-moving particles, suppresses the formation of low-mass halos, leading to fewer small primordial gas clouds. This suppression could be reflected in observations of the faintest galaxies and the structure of the intergalactic medium. By studying the statistical properties and spatial distribution of primordial gas clouds through absorption studies and simulations, astronomers aim to constrain the properties of dark matter indirectly. This approach connects the grand cosmic puzzle of dark matter to the intimate details of gas cloud physics. Primordial gas clouds also serve as fertile grounds to test fundamental physics under extreme conditions. In the early universe, the gas was subject to intense radiation backgrounds, high-energy particles, and rapidly changing environments. Studying these clouds can probe the behavior of atomic and molecular processes under low metallicity, low density, and high radiation conditions rarely encountered elsewhere. For example, the formation and destruction rates of molecular hydrogen, the key coolant in primordial gas, depend on subtle quantum mechanical processes, radiation fields, and dust grain abundance, which were practically absent in the early universe. Understanding these processes with precision is crucial, as small variations can have outsized effects on the thermal history and fragmentation of gas clouds. Laboratory experiments and quantum chemical calculations complement astronomical observations and simulations, forming a comprehensive picture of primordial gas cloud physics. From an observational standpoint, new techniques and instruments are opening unprecedented windows into these ancient clouds. 21 cm cosmology, the study of the hyperfine transition line of neutral hydrogen at radio wavelengths, promises to map the distribution of primordial gas across cosmic time. Unlike optical or infrared observations, which often capture only luminous sources, 21 cm signals can trace the vast reservoirs of neutral hydrogen gas, including primordial clouds, even before the first stars formed. Large radio interferometers like the Hydrogen Epoch of Reionization Array, HERA, and the upcoming Square Kilometer Array, SKA, are designed to detect the faint fluctuations in the 21 cm background caused by density variations, temperature changes, and ionization fronts in primordial gas clouds. These observations will yield 3D maps of gas distribution, allowing scientists to watch the cosmic dawn and reionization unfold in real time, testing models of primordial gas cloud formation and evolution. In the distant future, next-generation observatories may even detect faint emission lines from primordial gas clouds themselves. For example, emissions from molecular hydrogen, though challenging to detect due to the cloud's low metallicity and temperature, could provide direct evidence of gas cooling processes. Similarly, absorption studies of distant quasars' spectra may uncover signatures of primordial gas clouds through unique chemical fingerprints and line ratios, further illuminating the conditions of the early universe. The philosophical implications of studying primordial gas clouds are profound. They are not just astrophysical objects but cosmic archives, containing information about the universe's infancy, the laws of physics under primordial conditions, and the origins of complexity. Through their study, we trace the path from the almost uniform primordial plasma after the Big Bang to the rich diversity of galaxies, stars, planets, and eventually life itself. The ongoing pursuit to understand primordial gas clouds exemplifies the synergy between observation, theory, and simulation. It is a testament to humanity's desire to reach back across billions of years, to uncover the faint whispers of creation etched in hydrogen and helium gas. As we push the boundaries of knowledge, each discovery about these ancient clouds brings us closer to answering fundamental questions. How did the first light in the universe ignite? What processes forged the first heavy elements? How did cosmic structure emerge from primordial simplicity? As this quest continues, we remain humbled by the vastness and complexity of the cosmos, yet inspired by the persistent clues carried by primordial gas clouds. They are the silent witnesses to the dawn of time, inviting us to listen and learn from their ancient tales. The study of primordial gas clouds is also deeply connected to understanding the epoch of reionization, a transformative period in cosmic history when the neutral hydrogen in the intergalactic medium was ionized by the first luminous sources. This era, occurring roughly between 400 million to 1 billion years after the Big Bang, marks the universe's transition from darkness into the light-filled cosmos we observe today. Primordial gas clouds played a pivotal role in this process, both as the birthplaces of the first stars and galaxies and as reservoirs of neutral hydrogen that were gradually ionized. During the epoch of reionization, intense ultraviolet radiation from early stars, galaxies, and possibly accreting black holes began to carve out ionized bubbles within the pervasive neutral gas. These ionized regions expanded and eventually overlapped, completing the reionization of the universe. Primordial gas clouds, initially neutral and cold, were transformed by this radiation, heating up and becoming ionized. Understanding the properties of these clouds before, during, and after reionization offers critical insights into the timeline, sources, and mechanics of this cosmic phase change. Observations of high redshift quasars provide a window into this epoch by revealing the so-called Gunn-Peterson trough, a feature in quasar spectra caused by absorption of ultraviolet light by neutral hydrogen in primordial gas clouds. The disappearance or weakening of this trough at certain redshifts indicates the progression of reionization. Meanwhile, measurements of the cosmic microwave background polarization provide complementary constraints on the timing and duration of reionization, indirectly informing models of primordial gas cloud evolution. One of the most fascinating puzzles relates to the clumpiness of primordial gas clouds during reionization. The spatial distribution and density variations affect how quickly ionizing photons can escape from galaxies and penetrate the intergalactic medium. Highly clumped gas clouds can shield regions from ionizing radiation, delaying reionization locally, while more diffuse gas allows photons to travel further. Simulating this complex interaction between radiation and gas clouds requires advanced computational techniques, including radiative transfer coupled with hydrodynamics, and remains a frontier of theoretical astrophysics. In addition to their role in reionization, primordial gas clouds are central to the formation of the first population 3 stars, the first generation of stars formed from pristine, metal-free gas. These stars are theorized to be significantly more massive than typical stars today, with masses ranging from tens to hundreds of times that of the Sun. Their massive nature results from the limited cooling mechanisms available in primordial gas clouds, primarily molecular hydrogen cooling, which was less efficient than metal line cooling. Population 3 stars had brief but dramatic lives, rapidly exhausting their nuclear fuel and ending as energetic supernovae or direct black hole collapses. The feedback from these stars, through radiation, stellar winds, and supernova explosions, had profound effects on surrounding primordial gas clouds. They enriched the gas with the first heavy elements, altering its cooling properties and paving the way for subsequent generations of stars, population 2 and I, with different characteristics. The chemical signatures of population 3 stars are expected to be preserved in the gas clouds and stars formed shortly afterward. Detecting these signatures, such as unusual abundance patterns and extremely metal-poor stars within our galaxy, offers indirect evidence of primordial star formation processes. These observations help reconstruct the history and properties of primordial gas clouds that hosted the first stars. Another layer of complexity arises from the influence of cosmic magnetic fields on primordial gas clouds. Although the origin and strength of magnetic fields in the early universe remain uncertain, they can affect gas dynamics, fragmentation, and star formation. Even weak magnetic fields can influence the transport of angular momentum and the formation of protostellar disks within collapsing gas clouds. Understanding their role requires coupling magnetohydrodynamics with detailed chemical and radiative processes, adding to the challenge of modeling primordial gas clouds accurately. The dynamic environment of primordial gas clouds also sets the stage for the formation of the first galaxies, which began as small protogalactic clumps of gas and dark matter. These early galaxies were markedly different from the mature spiral and elliptical galaxies seen today. Their shallow gravitational potential wells made them vulnerable to feedback effects, leading to bursty and inefficient star formation. Observing these faint, distant galaxies with powerful telescopes such as the James Webb Space Telescope is beginning to shed light on how primordial gas clouds transitioned into structured galaxies. Furthermore, primordial gas clouds provide clues about the cosmic baryon budget, the distribution of ordinary matter in the universe. While dark matter dominates the mass, baryonic matter in the form of gas, stars, and galaxies constitutes the visible universe. However, observations indicate a discrepancy between the baryon density predicted by cosmological models and the baryons actually detected in stars and gas within galaxies. Much of the missing baryons are thought to reside in diffuse primordial and intergalactic gas clouds, either in warm hot phases or as cold filaments in the cosmic web. Detecting and characterizing these reservoirs remains an ongoing challenge, essential for completing our census of cosmic matter. The story of primordial gas clouds is also entwined with the quest to understand cosmic inflation and the initial conditions of the universe. The small fluctuations in density imprinted during inflation set the seeds for the formation of gas clouds and large-scale structure. Studying the distribution, properties, and evolution of primordial gas clouds thus offers an indirect window into the physics of the very early universe, potentially constraining inflationary models and the nature of primordial perturbations. As our observational capabilities continue to advance, the next decades promise unprecedented insights into primordial gas clouds. Upcoming space missions, advanced ground-based observatories, and next-generation computational simulations will work in concert to unravel the physics of these ancient reservoirs of matter. Through them, we seek to complete our understanding of how the cosmos evolved from a nearly uniform gas to the richly structured universe we inhabit today. In essence, primordial gas clouds are the foundational structures of cosmic history, repositories of information, engines of star and galaxy formation, and tracers of fundamental physics. Their mysteries are vast, their implications profound. By peeling back the layers of time and space encoded within these ancient clouds, humanity moves closer to answering the ultimate questions about our cosmic origins. Peering even deeper into the enigma of primordial gas clouds, one finds that these ancient formations hold keys to understanding the processes of cosmic chemical evolution, the gradual enrichment of the universe with elements heavier than hydrogen and helium. In the earliest epochs, the primordial gas was essentially devoid of metals, which astronomers define as all elements heavier than helium. This pristine composition set the stage for a universe where the first stars and galaxies formed under conditions fundamentally different from those prevalent today. The initial lack of metals in primordial gas clouds severely limited their ability to cool efficiently, as cooling channels through atomic and molecular transitions involving heavier elements simply did not exist. Molecular hydrogen, H2, became the primary coolant, but its formation was an intricate process dependent on the trace amounts of free electrons left over from recombination. These electrons catalyzed reactions that allowed H2 to form, despite the extremely low density and temperature of the early gas. The resulting cooling allowed gas clouds to contract under gravity and ultimately form the first stars. Once these population 3 stars ignited, their nuclear fusion processes forged the first heavy elements, which were subsequently dispersed into the surrounding gas through supernova explosions. This enrichment drastically changed the nature of gas clouds, increasing their metal content and enabling new, more efficient cooling mechanisms through atomic and dust emission. The transition from primordial, metal-free gas clouds to metal-enriched ones marked a watershed moment in cosmic history, setting the stage for the formation of the diverse galaxies, star clusters, and planetary systems we observe today. The interplay between primordial gas clouds and this chemical evolution is complex and ongoing. Certain regions of space, even billions of years later, preserve pockets of relatively metal-poor gas that serve as fossil records of early cosmic conditions. Studying these pockets helps astronomers reconstruct the timeline of metal enrichment, the efficiency of mixing processes in the intergalactic medium, and the rate of star formation in early galaxies. The complexity deepens when considering the role of turbulence and shock waves in primordial gas clouds. Unlike the calm, often idealized scenarios of gravitational collapse, real gas clouds are subject to turbulent motions driven by a variety of mechanisms, including gravitational instabilities, feedback from nascent stars, and large-scale cosmic flows. These turbulent motions can fragment the gas clouds, creating a hierarchy of density fluctuations that influence where and when stars form. Shock waves generated by supernova explosions and galaxy mergers can compress gas clouds, triggering new bursts of star formation or, conversely, dispersing the clouds and halting the process. Understanding these hydrodynamic processes in the primordial context is critical, as they determine the mass function of the first stars, the formation efficiency of early galaxies, and the propagation of ionizing radiation during reionization. Modern simulations of primordial gas clouds now incorporate these complex physics, revealing a dynamic and chaotic early universe far from the smooth, homogeneous picture once imagined. The potential presence of exotic physics in primordial gas clouds is another frontier of exploration. The early universe's unique conditions may have allowed for processes or particles beyond the standard model of physics to influence gas cloud behavior. For example, the annihilation or decay of dark matter particles within dense gas clouds could inject energy, heating the gas and altering star formation pathways. Similarly, hypothetical particles such as axions or sterile neutrinos might interact subtly with the gas, leaving imprints in the thermal history or chemical composition. While currently speculative, such possibilities motivate astronomers and physicists to seek subtle signatures in observations and simulations. Any detection of anomalous behavior in primordial gas clouds could provide indirect evidence of new physics, connecting cosmology, particle physics, and astrophysics in a profound way. On the observational side, the challenge of directly detecting primordial gas clouds lies in their faintness and distance. Their low temperatures and lack of metals mean they emit very little light, especially in visible wavelengths. Instead, astronomers rely on indirect techniques such as absorption spectroscopy, where the light from bright background objects, like quasars, is filtered through intervening gas clouds, imprinting characteristic absorption lines. These absorption line systems, categorized as Lyman-alpha forests, damped Lyman-alpha systems, and Lyman limit systems depending on their hydrogen column density, provide crucial clues about the properties of primordial and near-primordial gas clouds across cosmic time. The statistical study of these systems allows reconstruction of the density, temperature, velocity, and chemical composition of gas clouds, offering a window into their evolution and their role in galaxy formation. Technological advances in instrumentation and observational techniques continually improve our ability to study these absorption features. High-resolution spectrographs on large ground-based telescopes and space observatories now reveal unprecedented details in the spectra of distant quasars and gamma-ray bursts, enabling studies of primordial gas clouds billions of light-years away. The synergy between these observations and cutting-edge simulations, incorporating detailed physics of gas dynamics, chemistry, radiation, and gravity, forms the backbone of modern research into primordial gas clouds. These simulations, run on supercomputers, allows scientists to explore a vast parameter space, testing different scenarios of cosmic evolution and making predictions that can be confronted with observations. Looking forward, upcoming facilities such as the Extremely Large Telescope, ELT, the James Webb Space Telescope, JWST, and the Square Kilometer Array, SKA, promise to revolutionize our understanding of primordial gas clouds. JWST's infrared sensitivity will allow direct imaging and spectroscopy of the earliest galaxies and their gas reservoirs, while SKA's radio capabilities will map neutral hydrogen through the 21 cm line across cosmic epochs, illuminating the large-scale structure of primordial gas. Primordial gas clouds are the keystones of cosmic history. They encapsulate the transition from the simplicity of the early universe's hydrogen and helium soup to the complexity of galaxies, stars, and planets. Studying them bridges disciplines, linking fundamental physics, astrophysics, cosmology, and observational astronomy. As we deepen our exploration of these ancient, elusive clouds, we edge ever closer to answering the profound question of how the cosmos transformed from primordial chaos to the magnificent tapestry we observe today. The importance of primordial gas clouds extends beyond their role as mere star nurseries. They are crucial actors in the grand narrative of cosmic structure formation. Their interaction with dark matter, the mysterious substance that constitutes approximately 85% of the universe's matter content, is a cornerstone of modern cosmology. Primordial gas clouds formed within the gravitational wells created by dark matter halos, which acted as scaffolding for baryonic matter to accumulate and condense. The intricate dance between dark matter and ordinary gas shaped the universe's large-scale filamentary structure known as the cosmic web. Within this cosmic web, primordial gas clouds trace the filamentary filaments and nodes where galaxy clusters form. Understanding how gas flows along these structures, how it cools and collapses into galaxies, and how feedback from star formation and active galactic nuclei modulates this process remains one of the great challenges in astrophysics. Observations of primordial gas clouds in the intergalactic medium, alongside hydrodynamic simulations, provide key insights into these mechanisms. Moreover, primordial gas clouds offer a laboratory to test the fundamental constants of nature and their potential variation over cosmic time. Since these clouds existed at epochs close to the beginning of the universe, studying the absorption lines they imprint on background quasar light enables measurements of atomic transitions under vastly different physical conditions than those in the present universe. Precise measurements have been used to test whether constants such as the fine structure constant or the proton-to-electron mass ratio have varied over billions of years, which would have profound implications for physics. Another tantalizing prospect involves the detection of primordial molecules beyond molecular hydrogen, such as deuterium hydride, HD, helium hydride ion, HE, and lithium hydride, LiH. These molecules are predicted to form in trace amounts in the early universe and can provide unique fingerprints of primordial chemistry. The recent detection of HE in a planetary nebula within our galaxy marked a milestone, confirming theoretical predictions, and has sparked efforts to detect such molecules in primordial gas clouds at high redshift. The thermal history of primordial gas clouds also offers critical clues about the nature of the cosmic microwave background, CMB, radiation and the formation of the first luminous objects. The interplay between the cooling of gas clouds and heating by CMB photons imposes a minimum temperature floor, influencing the mass scale of the first collapsing objects. This delicate balance affects when and how the first stars ignited, which in turn affected the timing and progression of reionization. The advent of the 21 cm hydrogen line as a probe of primordial gas clouds has revolutionized the field. This spectral line, arising from the hyperfine transition of neutral hydrogen, allows astronomers to map the distribution and state of hydrogen gas across cosmic time. By observing redshifted 21 cm signals, scientists can chart the density, temperature, and ionization state of primordial gas clouds from the cosmic dawn through the epoch of reionization and beyond. Efforts such as the Hydrogen Epoch of Reionization Array, HERA, and the Low Frequency Array, LOFAR, are pushing the limits of sensitivity and resolution to detect this faint signal. Success in this endeavor will open a new window into the early universe, enabling 3D tomographic imaging of the primordial gas distribution and its evolution. The mysterious dark ages of the universe, the period after recombination and before the first stars formed, is dominated by primordial gas clouds. During this era, the universe was filled with cold, neutral hydrogen and helium gas, and devoid of luminous sources. This era remains observationally elusive, but understanding the physical state and evolution of primordial gas clouds during this time is crucial for a complete picture of cosmic history. The nature of primordial gas clouds is also intrinsically linked to the question of dark matter particle properties. If dark matter consists of weakly interacting massive particles, WIMPs, or other candidates that can annihilate or decay, the energy injected into primordial gas clouds would alter their temperature and ionization state, impacting star formation. This indirect probe offers a novel way to constrain dark matter models through astrophysical observations. In some speculative models, primordial gas clouds might harbor primordial black holes, hypothetical black holes formed in the early universe from density fluctuations. If they exist, these black holes could influence the dynamics and evolution of gas clouds, act as seeds for supermassive black holes found at galactic centers, and contribute to dark matter. Detecting their influence on gas clouds or through gravitational wave observations remains a frontier area of research. In terms of observational frontiers, the combination of multi-wavelength astronomy, from radio to infrared to X-rays, is essential to characterize primordial gas clouds comprehensively. Each wavelength probes different physical processes. Radio reveals cold neutral hydrogen, infrared captures the emission from dust and molecules, ultraviolet traces ionized gas, and X-rays detect high-energy phenomena like black hole accretion. As technology advances, the synergy between observations and theoretical modeling grows ever more powerful. The next generation of telescopes will not only detect primordial gas clouds with greater clarity, but also unravel their internal structure, chemistry, kinematics, and interactions with radiation and dark matter. This holistic understanding is crucial for piecing together the cosmic puzzle from the universe's infancy to its present grandeur. Primordial gas clouds are not just relics of an ancient cosmos. They are dynamic, evolving entities central to the universe's story. They connect the dots from fundamental physics and early universe cosmology to galaxy formation and cosmic evolution. Exploring their mysteries is a journey through time and space, unveiling the very origins of structure, matter, and light in our universe. The quest to understand primordial gas clouds also intersects profoundly with the investigation of cosmic feedback mechanisms, the processes by which energy and matter expelled by stars, supernovae, and active galactic nuclei influence their surroundings. In the nascent universe, feedback from the first generations of stars, born within primordial gas clouds, profoundly reshaped their environments. This feedback could either trigger new rounds of star formation by compressing nearby gas or suppress it by heating and dispersing the gas clouds. The delicate balance of feedback effects dictated the pace of early galaxy assembly and the progression of cosmic reionization. Powerful outflows from massive population 3 stars and their supernova explosions could clear out vast cavities in the intergalactic medium, creating channels through which ionizing photons escape to reionize the universe. At the same time, these energetic events enrich the gas with metals, fundamentally changing the thermodynamics of subsequent gas clouds. Understanding these feedback cycles is vital for building accurate models of early cosmic structure formation. They introduce nonlinear and chaotic behaviors that complicate predictions and simulations but are necessary for reconciling observations of early galaxies with theory. The complex physics involved, radiation hydrodynamics, chemical enrichment, magnetohydrodynamics, require cutting-edge computational methods and immense computational resources. Moreover, primordial gas clouds hold clues about the formation of supermassive black holes, SMBHs, enigmatic objects with masses millions to billions of times that of the Sun, residing in the centers of most galaxies. Observations have revealed SMBHs existing less than 1 billion years after the Big Bang, posing a challenge to standard growth models. One leading hypothesis suggests that some primordial gas clouds underwent direct collapse, bypassing star formation, and formed massive black hole seeds rapidly. These direct collapse black holes could form from massive, metal-poor gas clouds that avoided fragmentation and cooled inefficiently, allowing large amounts of gas to funnel into a single dense core that collapsed under its own gravity. The radiation and dynamics of these clouds during collapse remain active areas of theoretical study, as understanding these processes is key to explaining the early appearance of SMBHs. In addition to their astrophysical significance, primordial gas clouds offer a unique environment to study fundamental chemistry under extreme conditions. The low metallicity, intense radiation fields, and dynamic densities create regimes inaccessible on Earth. Reactions involving molecular hydrogen, ions, and trace molecules proceed under conditions of low temperature and density, shaping the gas cooling and cloud evolution. Laboratory astrophysics experiments and quantum chemistry calculations complement astronomical observations to refine reaction rates and molecular data crucial for modeling. The presence and role of dust grains, tiny solid particles formed from heavy elements, in primordial gas clouds is another frontier. Initially absent in pristine gas, dust formation commenced after the first supernovae polluted the environment. Dust facilitates cooling, acts as a catalyst for molecule formation, and influences the opacity of the gas, thus impacting star formation. Studying the emergence and impact of dust bridges cosmic chemistry with stellar evolution and interstellar medium physics. The complex morphology of primordial gas clouds also challenges astronomers. Observations and simulations reveal that these clouds are not uniform blobs but exhibit filamentary structures, knots, and sheets shaped by gravity, turbulence, magnetic fields, and radiation pressure. These structures determine the initial mass function of stars, the distribution of stellar masses at birth, which in turn affects galaxy evolution and feedback processes. From a cosmological perspective, primordial gas clouds serve as cosmic signposts for testing dark energy models and the universe's expansion history. By mapping their distribution and properties at different redshifts, astronomers can measure the growth of large-scale structure over time. These measurements provide constraints on the nature of dark energy, the mysterious force driving the universe's accelerated expansion. The pursuit to unravel the secrets of primordial gas clouds also inspires the development of novel observational techniques. Techniques such as intensity mapping, which measure the integrated emission of spectral lines over large volumes without resolving individual sources, hold promise for detecting faint signals from these early clouds across cosmic time. In the context of education and public engagement, primordial gas clouds embody the poetic origins of the universe. They connect the physics of the infinitesimally small, quantum reactions and atomic transitions, with the vast scales of cosmology and galactic evolution. Sharing their story illuminates the interconnectedness of natural phenomena and humanity's place in the cosmos. Primordial gas clouds stand as fundamental cosmic actors shaping the trajectory of the universe. Their study synthesizes multiple disciplines and techniques, from observational astronomy and theoretical physics to chemistry and computational science. As technology and theory advance hand in hand, the mysteries of these ancient clouds will gradually unfold, offering profound insights into the origins of matter, structure, and life itself. Delving further into the nature of primordial gas clouds, one must consider their role in shaping the cosmic microwave background, CMB, anisotropies we observe today. The subtle temperature fluctuations in the CMB encode information about the density variations of baryonic matter, ordinary matter composed of protons and neutrons, just before the epoch of recombination. These primordial fluctuations provided the seeds for gas clouds to coalesce under gravity. By studying these anisotropies with exquisite precision, missions like COBE, WMAP, and Planck have offered insights into the initial conditions that govern the formation and evolution of primordial gas clouds. The subsequent growth of these gas clouds, influenced by both gravity and pressure forces, is a delicate interplay often described by the Jeans instability criterion. This criterion determines the critical size or mass above which a gas cloud becomes gravitationally unstable and begins to collapse. In the early universe, The gene's mass was significantly larger due to the higher temperature of the gas and the lack of efficient cooling mechanisms, implying that the first star-forming clouds were massive, much more so than typical molecular clouds in today's galaxies. This early stage set the cosmic stage for the formation of population 3 stars, the very first generation of stars. These stars formed almost exclusively from primordial gas clouds, thus lacking metals entirely. Their properties, mass, luminosity, lifespan, are subjects of intense research. Simulations suggest they were typically very massive, some exceeding hundreds of solar masses, burning hot and fast. Their radiative output, supernova explosions, and eventual black hole remnants profoundly affected the surrounding primordial gas clouds, reionizing and enriching the universe in metals. The feedback from population 3 stars also had the potential to halt further star formation temporarily by heating and dispersing nearby gas clouds. However, in some cases, their explosive deaths could compress adjacent gas clouds, triggering new star formation episodes, a cosmic cycle of destruction and creation originating in these primordial clouds. One of the more intriguing aspects of primordial gas clouds is their potential connection to the mysterious dark matter. While dark matter does not interact electromagnetically and is invisible, its gravitational influence profoundly affects gas cloud formation. The earliest gas clouds formed within the potential wells of dark matter halos. The size, shape, and distribution of these halos dictated where gas clouds could condense and form stars. The precise nature of dark matter, whether cold, warm, or self-interacting, modifies these halos' characteristics and thus the properties of primordial gas clouds. Current research employs high-resolution cosmological simulations incorporating both dark matter and baryonic physics to explore these interactions. Such simulations reveal the emergence of the cosmic web, a vast network of filaments and nodes where gas clouds accumulate and galaxies eventually form. The gas within these filaments remains relatively pristine, offering possible sites to observe primordial gas clouds even at later cosmic times. Moreover, the study of primordial gas clouds intersects with investigations into cosmic reionization, a major phase transition in the universe's history. After recombination, the universe was neutral and dark. The birth of the first luminous objects, ignited within primordial gas clouds, produced energetic ultraviolet photons that gradually reionized hydrogen in the intergalactic medium. Tracing this epoch requires understanding how primordial gas clouds formed stars, how those stars emitted radiation, and how the gas was heated and ionized. This epoch is indirectly probed by observations of distant quasars and galaxies, whose spectra exhibit absorption features revealing the ionization state of intervening gas clouds. The timeline and topology of reionization remain active research frontiers, with primordial gas clouds at their core. Recent advances in radio astronomy offer the promise of directly imaging neutral hydrogen gas during this epoch via the 21 cm line. By mapping the faint signals of neutral hydrogen absorption and emission, astronomers hope to reconstruct the three-dimensional structure and evolution of primordial gas clouds and the progression of reionization. Instruments such as the Square Kilometer Array, SK, and Hydrogen Epoch of Reionization Array, HERA, are pioneering this field. At the molecular level, primordial gas clouds reveal a rich, though sparse, chemistry. Although dominated by hydrogen and helium, trace molecules like molecular hydrogen, H2, deuterated hydrogen, HD, helium hydride ion, HH, and lithium hydride, LiH, play outsized roles in gas cooling and star formation. These molecules form through a complex network of reactions catalyzed by free electrons and ions present in the gas. Detecting these molecules in primordial gas clouds provides critical tests of chemical models and offers clues about the cooling pathways that enabled the first stars to form. For instance, HH, theorized as the universe's first molecule, was recently detected in a planetary nebula, confirming long-standing predictions. Efforts continue to identify such molecules in primordial environments, opening windows into the earliest chemical processes. On the observational frontier, detecting primordial gas clouds directly remains challenging due to their faintness and distance. However, Absorption line spectroscopy against bright background sources such as quasars offers a powerful tool. The Lyman alpha forest, a dense series of absorption lines in quasar spectra, traces intervening hydrogen gas clouds, many of which retain primordial or near-primordial compositions. The statistical properties of these absorption systems inform us about gas cloud distribution, density, temperature, and ionization. These absorption studies also shed light on the metallicity of gas clouds, revealing how the universe's first stars enriched their surroundings. Some gas clouds show extremely low metal content, hinting they may be relics of primordial gas that escaped contamination, while others reveal progressive enrichment patterns. The nature of primordial gas clouds also poses profound questions about initial mass functions, IMFs, and star formation efficiency. The IMF describes the distribution of stellar masses formed from a gas cloud. In the primordial context, the IMF likely favored massive stars, whereas in the present-day universe, it is weighted towards smaller stars. This difference has cascading consequences for galaxy evolution, feedback, and chemical enrichment. Understanding the physical conditions, temperature, density, turbulence, magnetic fields, that regulated star formation in primordial gas clouds is thus essential. Recent simulations incorporating radiation hydrodynamics, non-equilibrium chemistry, and magnetohydrodynamics strive to capture this complexity, offering predictions for the mass and luminosity distribution of the first stars and galaxies. Primordial gas clouds are not mere cosmic relics but dynamic, fundamental components shaping the universe's infancy and evolution. Their study weaves together cosmology, astrophysics, chemistry, and fundamental physics. As observations improve and theories advance, they remain a frontier promising to unlock secrets about the origin of structure, the nature of dark matter, the first stars and galaxies, and the cosmic environment that ultimately gave rise to life itself. The narrative of primordial gas clouds inevitably leads us to the fascinating question of their role in galaxy formation and evolution. These ancient clouds were the raw material from which the first galaxies coalesced, dictating the initial conditions and subsequent pathways of cosmic structure assembly. The gravitational collapse of these clouds, under the influence of dark matter halos, resulted in the first starburst events, which gradually built up the stellar populations and interstellar media that characterize galaxies today. Understanding how primordial gas clouds fragmented and collapsed is key to unraveling the morphology and mass distribution of early galaxies. Some clouds fragmented into numerous smaller clumps, giving rise to star clusters and protogalactic structures, while others may have undergone more monolithic collapse, potentially explaining the formation of massive elliptical galaxies observed at high redshift. The interplay of cooling processes, turbulence, magnetic fields, and feedback from the earliest stars determined the fate of these clouds and the nature of the galaxies that formed. An exciting facet of current research focuses on the detection of cold streams of primordial gas feeding growing galaxies. Contrary to the traditional view where galaxies accrete gas primarily through mergers and hot accretion, simulations suggest that cold, dense gas can flow along cosmic filaments directly into galaxies. These streams maintain low temperatures due to the pristine nature of the gas and its high density, enabling efficient star formation and rapid galaxy growth. Observational evidence of such cold accretion is emerging through spectral signatures and absorption studies, further highlighting the importance of primordial gas and galaxy evolution. In the cosmic timeline, the transition from primordial gas clouds to metal-enriched environments marks a pivotal era, known as chemical enrichment. The first supernovae explosions dispersed heavy elements synthesized in massive stars into surrounding gas clouds, altering their cooling properties and chemistry. This process enabled the formation of population II stars with progressively higher metallicity, bridging the gap between the primordial universe and the chemically rich cosmos we inhabit. This enrichment process is traced through the observation of extremely metal-poor stars and gas clouds in the Milky Way and distant galaxies, offering fossil records of primordial gas conditions. These ancient stars preserve the nucleosynthetic signatures of the first supernovae and provide constraints on the initial mass function and explosion mechanisms of population III stars. Similarly, metal-poor damp Lyman alpha systems, DLAs, and Lyman limit systems and quasar absorption spectra provide insights into the composition and distribution of primordial and early enriched gas clouds. The complex interplay of star formation, feedback, chemical enrichment, and gas accretion within primordial gas clouds also has implications for the formation of planetary systems and the origins of life. While the primordial clouds themselves were devoid of metals and complex molecules necessary for planet formation, their evolution set the stage for subsequent generations of star and planet formation. The dispersal of heavy elements and dust into the interstellar medium created environments conducive to the formation of rocky planets and organic chemistry. On the theoretical front, advances in cosmological simulations incorporating increasingly sophisticated physics, non-equilibrium chemistry, radiative transfer, magnetohydrodynamics, and cosmic ray feedback have enabled detailed studies of primordial gas cloud formation and evolution. These simulations span vast dynamic ranges, capturing processes from cosmological scales down to the intricate collapse of individual gas clumps. Such models provide testable predictions for observations, guiding the search for primordial gas signatures and informing our understanding of early universe physics. The ongoing development of new observatories promises to revolutionize our understanding of primordial gas clouds. The James Webb Space Telescope, JWST, with its unprecedented sensitivity in the infrared, aims to observe the first galaxies and the signatures of primordial gas cooling and star formation. The detection of emission lines from primordial gas clouds, such as Lyman alpha and molecular hydrogen lines, will shed light on their physical conditions and star-forming activities. Similarly, next-generation ground-based telescopes like the Extremely Large Telescope, ELT, and the 30-meter telescope, TMT, will provide high-resolution spectroscopy to dissect the composition and dynamics of distant primordial gas clouds. Coupled with radio observatories probing the 21 cm line and millimeter wave facilities detecting molecular lines, a multi-wavelength, multi-messenger approach will emerge to fully characterize these cosmic entities. Fundamentally, primordial gas clouds embody the universe's earliest chapters, a time when matter and energy, governed by the fundamental forces, organized into the complex tapestry of stars, galaxies, and ultimately life. Their study not only addresses scientific curiosity but touches upon philosophical questions about origins and existence, linking humanity's quest to understand the cosmos with the very building blocks that enabled our emergence. As we gaze deeper into the cosmos and further back in time, primordial gas clouds remain both a challenge and a guide, whispering secrets from an era when the universe was young and pristine, inviting us to uncover the genesis of all cosmic structure. Exploring even deeper, primordial gas clouds compel us to consider the subtle interplay between magnetic fields and turbulence in the early universe. While primordial gas is often assumed to be nearly magnetically neutral at the onset, various mechanisms could generate seed magnetic fields, such as the Biermann battery effect or turbulence induced by structure formation shocks. Once present, even weak magnetic fields can be amplified dramatically through turbulent dynamo processes as gas clouds collapse and fragment. Magnetic fields influence the angular momentum transport and fragmentation scale of collapsing clouds, thereby affecting star formation efficiency and the mass distribution of newborn stars. They also provide pressure support against gravity, potentially delaying or suppressing collapse in some regions. Observationally, the detection of magnetic fields in high redshift environments remains challenging but could be achieved through measurements of polarized emission or Faraday rotation in future facilities. Turbulence within primordial gas clouds adds further complexity. Originating from gravitational instabilities, accretion flows, and feedback from the first stars, turbulence injects kinetic energy across multiple scales, creating a chaotic, clumpy medium. This turbulence regulates the balance between gas cooling and heating, influencing cloud fragmentation and the formation of stellar clusters versus isolated massive stars. The thermal evolution of primordial gas clouds is governed by a race between cooling mechanisms, mainly molecular hydrogen emission, and heating from gravitational compression, cosmic rays, and ultraviolet radiation. The lack of metals and dust in pristine gas limits cooling channels, meaning gas must reach higher densities and temperatures to overcome pressure support and fragment. This condition favors the formation of massive stars, which produce copious ionizing radiation, shaping their environment. The complex chemistry within these clouds is driven not only by hydrogen and helium reactions but also by trace species like HD, deuterium hydride, which can become dominant coolants under certain conditions. The balance of these molecular coolants determines whether a cloud fragments into many smaller clumps or remains coherent, forming one or a few massive stars. Moreover, the potential presence of exotic physics in primordial gas clouds has been proposed as a frontier in cosmology. Hypothetical particles such as sterile neutrinos or axions could interact weakly with baryonic matter, subtly altering gas cooling or collapse dynamics. While purely speculative, these possibilities highlight the role of primordial gas clouds as cosmic laboratories probing physics beyond the standard model. The interaction of primordial gas clouds with radiation backgrounds, both cosmic microwave and ultraviolet, further complicates their evolution. The ultraviolet radiation from the first stars can dissociate molecular hydrogen, the primary coolant, in nearby clouds, suppressing star formation in a process called radiative feedback or Lyman-Werner feedback. This creates a patchwork of star-forming and star-suppressed regions, influencing the topology of cosmic reionization. Conversely, cosmic rays and X-rays produced by early supernovae and accreting black holes can ionize gas within primordial clouds, enhancing molecular formation rates and promoting cooling, thus enabling star formation in otherwise hostile environments. The balance between these competing effects governs the spatial and temporal pattern of early star formation and galaxy assembly. A particularly captivating mystery tied to primordial gas clouds is their connection to dark ages and the cosmic dawn, eras preceding and marking the emergence of the first luminous objects. During the dark ages, neutral hydrogen gas filled the universe, and primordial gas clouds formed slowly under gravity's pull. The cosmic dawn began as the first stars ignited, their radiation illuminating and transforming these clouds. Studying the 21 cm hyperfine transition of neutral hydrogen from this epoch promises to reveal the structure, temperature, and ionization state of primordial gas clouds on unprecedented scales. The spatial fluctuations in this signal reflect the distribution and evolution of these clouds, offering a direct probe of the universe's earliest astrophysical processes. On the observational frontier, the identification of extremely metal-poor galaxies and gas clouds serves as windows into primordial conditions. These systems, with metallicities just a fraction of the solar value, resemble the primordial gas clouds before widespread chemical enrichment. Detailed spectroscopic studies of their gas composition, star formation activity, and dynamics provide crucial insights into how primordial clouds evolved into the diverse cosmic structures we observe. In a more speculative vein, primordial gas clouds have been proposed as environments for primordial star clusters or globular cluster formation, offering clues to the oldest stellar populations and galaxies. The conditions within massive primordial clouds might have allowed the rapid formation of dense star clusters, which survive to the present day as ancient globular clusters, bearing chemical fingerprints of the early universe. Primordial gas clouds connect cosmological scales to fundamental constants and physical laws. Their formation and evolution depend on the values of constants such as the fine structure constant, proton-to-electron mass ratio, and nuclear reaction rates. Investigations into possible spatial or temporal variations of these constants often reference primordial cloud chemistry and cooling as sensitive probes, intertwining cosmology with fundamental physics. As our journey through the enigmatic realm of primordial gas clouds continues, it becomes clear that these ethereal clouds are not mere relics but vibrant actors in the cosmic saga. They bridge the gap from the Big Bang's initial simplicity to the rich complexity of the universe, embodying mysteries that challenge and inspire generations of astronomers, physicists, and thinkers. The potential of primordial gas clouds to unlock the deepest secrets of the universe extends into the realm of cosmic structure formation, where their properties and behaviors serve as the scaffolding for the entire cosmic web. These clouds did not form in isolation. Rather, they were strung along vast filaments of dark matter, feeding into the densest nodes where the first proto-galaxies were born. This network of interconnected filaments, sheets, and voids defines the large-scale structure of the universe and was seeded by the quantum fluctuations stretched across space during inflation. The gas flowing into these filaments from voids, much of it pristine and primordial, was gravitationally pulled into knots, where the density became high enough for gravitational collapse to commence. Here, primordial gas clouds formed under the pull of dark matter halos, often merging and mixing, creating increasingly complex dynamics. Their coalescence laid the foundations for galaxy clusters and superclusters, and the filamentary flows ensured a steady supply of fuel for ongoing star formation in early galaxies. What's particularly fascinating is that these clouds acted as cosmic time capsules. The composition of a gas cloud could remain relatively unchanged over hundreds of millions of years if isolated from nearby star-forming regions. Some clouds even today, particularly in the outskirts of galaxies or in intergalactic space, may preserve conditions remarkably close to primordial. Discovering and analyzing such clouds offers a glimpse into the state of the cosmos not long after the Big Bang. From an energetic perspective, the behavior of primordial gas clouds was profoundly influenced by cooling timescales versus dynamical timescales. The cooling timescale, how quickly a cloud could radiate away its heat, needed to be shorter than the free-fall time for collapse to proceed. Without metals and dust, this cooling was highly inefficient, relying on the rare molecular hydrogen and HD molecules. This inefficiency meant that only the largest clouds, with the deepest potential wells and highest densities, could collapse within the age of the universe at the time. This fact helps explain why the first star-forming halos had to reach a critical virial temperature, often estimated at around 10,000 Kelvin, the threshold for hydrogen atomic line cooling. Below this, gas clouds struggled to lose energy fast enough to condense. This bottleneck regulated the pace at which primordial stars could form and therefore paced the onset of reionization. Primordial gas clouds also present a curious aspect when considering the origin of massive black holes in the early universe. One of the unsolved mysteries in astrophysics is how supermassive black holes, billions of solar masses, appeared so early, within the first billion years after the Big Bang. One hypothesis involves the direct collapse of primordial gas clouds under specific conditions. If the cloud avoided fragmentation due to strong ultraviolet backgrounds that dissociated molecular hydrogen, it could collapse directly into a massive black hole seed, potentially tens of thousands of solar masses. These direct collapse black holes could then rapidly grow by accreting surrounding gas or merging with other black holes. This possibility makes primordial gas clouds a central component in solving the black hole formation mystery. Their cooling history, exposure to background radiation, and internal angular momentum all affect whether a cloud forms stars or collapses into a black hole. Observations of quasars at redshifts beyond 6, when the universe was under 1 billion years old, support the idea that some black holes grew unusually quickly, and primordial gas clouds likely played a key role. Yet another speculative but captivating idea involves the concept of primordial gas cloud collisions. In the early universe, when density fluctuations were more extreme and cloud populations more numerous, gas clouds could have collided at high velocities. These collisions might have triggered shock waves, compressing gas to the point where rapid starbursts occurred. Such events could also lead to large-scale outflows, enriching the intergalactic medium and possibly generating turbulence that would impact subsequent cloud evolution. The metallicity, or lack thereof, of these clouds continues to be a critical tracer of cosmic history. With each generation of star formation and supernovae, metals were added to the gas clouds. By analyzing the elemental abundances in different environments, like the ratios of carbon to oxygen, or the presence of rare elements like barium and europium, astronomers can infer the nucleosynthetic pathways that took place in the earliest stars. Some ancient stars show abundance patterns that strongly suggest they formed from gas enriched by only 1 or 2 previous supernovae. Essentially second-generation stars formed directly from primordial gas clouds tainted only slightly. In the vast cosmic ocean, there's also the idea that isolated primordial gas clouds could persist much longer than previously thought, especially in low-density regions of the universe far from star-forming galaxies. Some theoretical models even propose that small, metal-free clouds might survive to the present day, undisturbed and chemically untouched. If such a cloud could be found and analyzed, it would provide a pristine laboratory for testing Big Bang nucleosynthesis predictions directly, something no experiment on Earth could ever replicate. Adding another layer of intrigue, primordial gas clouds might also help answer questions about the universe's baryon asymmetry, why there is more matter than antimatter. While this is a problem deeply rooted in particle physics, understanding the detailed behavior of early baryonic matter, how it clustered, cooled, and formed structure, could provide indirect insights. Some theories propose exotic particle decays in the early universe or interactions involving dark matter that left a trace in the behavior of the earliest gas clouds. Precision measurements of these clouds might one day reveal subtle asymmetries encoded in their structure. And still, even with all this complexity, there's an almost poetic simplicity to primordial gas clouds. They are the first whisper of cosmic order rising out of chaos. They formed not out of coincidence, but from a finely balanced set of conditions that dictated how matter would gather and light would be born. In a universe initially filled with nothing but darkness and uniformity, these clouds introduce variety, potential, and evolution. As we refine our tools, both observational and theoretical, we move ever closer to truly resolving the life cycle of these primordial clouds, from their formation out of the Big Bang's debris to their transformation into the stars that lit up the cosmos. Each new discovery pushes the veil back just a little further, bringing us one step closer to a full cosmic narrative. The story of primordial gas clouds is ultimately the story of everything. Galaxies, stars, black holes, planets, life, it all begins in these delicate clouds of hydrogen and helium, adrift in the void, waiting for gravity to take hold. In tracing the journey of primordial gas clouds through the early cosmos, we find ourselves increasingly confronted with the profound interdependence between baryonic matter and dark matter. The visible components of the universe, those atoms of hydrogen and helium swirling in the vastness of early space, did not evolve in isolation. They were profoundly shaped by the invisible scaffolding of dark matter that shaped the contours of the young universe. These gas clouds, though governed by thermodynamics, cooling, and pressure forces, ultimately moved and collapsed under the gravitational influence of dark matter halos. The synergy between dark matter and baryons is one of the most fundamental relationships in cosmology. As dark matter halos grew through hierarchical merging and accretion, they pulled in gas from their surroundings. The denser the dark matter concentration, the deeper the gravitational well, and the more efficiently it could attract and retain gas. In regions where the density of dark matter was highest, primordial gas clouds condensed more quickly and intensely, giving rise to the first stars and galaxies. Interestingly, this process was not uniform. In some regions, the relative velocity between dark matter and baryons, residual from the decoupling era, was high enough to suppress gas accretion into dark matter halos, delaying structure formation. This phenomenon, known as baryon dark matter velocity offset, led to spatial variations in the timing and efficiency of the first star formation events. These offsets created cosmic patchiness, producing early voids and overdense regions that would later become galactic clusters. Beyond the direct gravitational pull, dark matter may have also indirectly influenced turbulence and fragmentation within primordial gas clouds. The small-scale granularity of dark matter halos could have created density perturbations within the gas, acting as seeds for turbulence and leading to a non-uniform, lumpy structure. This irregularity could have either accelerated or impeded the onset of star formation, depending on local conditions. As stars began to form within these clouds, their intense radiation, powerful winds, and explosive deaths as supernovae introduced a new actor into the gas cloud narrative: stellar feedback. This feedback shaped the fate of primordial clouds in dramatic ways. On one hand, the radiation pressure and shock waves from supernovae could disrupt clouds, halting further star formation. On the other hand, the compression from these same shockwaves could trigger new rounds of collapse in neighboring clouds. These feedback mechanisms also had implications on much larger scales. They drove outflows that expelled gas into the intergalactic medium, enriching it with the first heavy elements and redistributing energy and momentum on galactic scales. The chemical makeup of primordial clouds was thus not static. It was continuously shaped by a cosmic dialogue between collapsing clouds, newly born stars, and the violent events of stellar death. This process led to the emergence of a metallicity gradient in the early universe. Regions closer to early star-forming galaxies became progressively more enriched, while more isolated primordial clouds remained chemically pristine for much longer. This uneven chemical evolution provides today's astronomers with a natural laboratory. By studying extremely metal-poor stars and galaxies, we can reconstruct the chemical fingerprints left behind by these clouds and understand the nucleosynthetic history of the cosmos. The importance of primordial gas clouds extends even beyond their astrophysical contributions. They serve as powerful cosmological probes. Their properties encode information about the physics of the early universe, the composition of the primordial plasma, the timing of recombination, the strength of primordial magnetic fields, and the density fluctuations seeded by inflation. Even slight deviations in these physical conditions would have led to dramatically different cloud behaviors. For instance, a slightly higher baryon density would have led to faster cloud formation and earlier star formation, possibly altering the timeline of reionization and the formation of large-scale structure. Similarly, differences in the fine structure constant or electron mass would affect the cooling rates of primordial gas, influencing when and where stars could form. And then, there is the deep time implication of primordial molecular chemistry. The formation of molecular hydrogen in these clouds, through reactions involving free electrons and neutral hydrogen, was one of the first complex chemical processes in the cosmos. These early chemical pathways paved the way for more sophisticated chemistry later, including the formation of organic molecules in star-forming regions billions of years later. Though primordial gas clouds contain no carbon, nitrogen, or oxygen, the processes that unfolded within them laid the physical groundwork for future molecular complexity, and eventually for life. Some theorists have even suggested that exotic phenomena like primordial black holes, hypothetical black holes formed during the earliest moments of the universe, could interact with primordial gas clouds in detectable ways. As these black holes drift through the cosmos, they could accrete surrounding gas, leaving behind faint but distinct X-ray signatures or altering the thermal balance of nearby clouds. Detecting such interactions would not only reveal new physics but also shed light on one of the darkest corners of cosmology. Today, as we aim our most advanced instruments, like the James Webb Space Telescope, ALMA, and future observatories like the Square Kilometre Array, at the deep sky, we are, in essence, trying to listen to the echoes of these ancient gas clouds. We search for the faint redshifted Lyman alpha emissions, for absorption lines from neutral hydrogen, for temperature fluctuations in the 21 cm background, all fingerprints left by these elusive clouds. What we discover will likely refine our models of cosmic dawn, the birth of galaxies, the growth of black holes, and even the origin of matter itself. Primordial gas clouds, quiet and ancient, are among the most honest storytellers of the universe. They hold within them not only the past but the pathways that shaped everything that followed. Their silence is not emptiness, it is the silence before the first song of stars. As we gaze further into the depths of the universe, trying to peel back the layers of time and space, primordial gas clouds remain some of the most essential pieces in the cosmic puzzle. Their quiet existence in the early epochs of the universe was anything but simple. They were the battlegrounds where gravity, thermodynamics, radiation, and chemistry waged their first epic struggles to shape the cosmos. In many ways, these clouds acted as the great intermediaries, bridging the cold uniformity of the cosmic microwave background and the complex clumpiness of galaxies and stars. A key aspect that continues to intrigue scientists is the role of environment in determining the fate of a primordial gas cloud. Those forming in isolation, far from neighboring structures, had an entirely different evolution compared to those trapped in more crowded regions of the cosmic web. Isolated clouds could remain chemically untouched for hundreds of millions of years, possibly forming the last metal-free stars even as other parts of the universe had already entered a new age of chemical complexity. Meanwhile, clouds in high-density regions were often bombarded by radiation, heated by nearby star-forming galaxies, or compressed by gravitational interactions with growing dark matter halos. This environmental dependency is a core principle in modern astrophysics, especially in the study of cosmic variance. The idea that different regions of the universe can evolve at different rates based on their initial density fluctuations. It's why the universe did not reionize all at once, and why galaxies of the same age can appear drastically different depending on where they formed. Primordial gas clouds were subject to the same diversity of outcomes, despite originating from the same Big Bang conditions. And that diversity feeds into one of the most exciting frontiers of modern cosmology: the study of ultra-faint dwarf galaxies and ancient stellar populations. Some of these small, dim galaxies, discovered only recently, appear to be time capsules, entire systems that have not significantly evolved since the early universe. Their gas content, stellar mass, and metallicity profiles closely resemble what we would expect if they had formed directly from primordial clouds and remained relatively untouched. These galaxies, and the stars within them, allow researchers to reverse engineer the conditions that prevailed inside primordial gas clouds. The chemical fingerprints of stars within these systems show patterns consistent with enrichment from only one or two population 3 supernovae, pointing to an incredibly quiet and pristine history. It's almost as if these systems are fossil relics of the very first galactic structures, giving us a rare chance to observe primordial cloud evolution frozen in time. Beyond stellar populations and galactic archaeology, the mystery of primordial gas clouds extends into the realm of cosmic reionization, one of the most significant and least understood transitions in the history of the universe. This was the era when the ultraviolet light from the first stars and galaxies began ionizing the neutral hydrogen that filled the universe. The process did not happen uniformly. Instead, it unfolded as expanding bubbles of ionized gas grew around early star-forming regions, eventually overlapping to reionize the entire universe. Primordial gas clouds were both the fuel and the victims of this transformation. Those too close to strong ultraviolet sources were photoevaporated, their gas ionized and driven away before it could collapse into stars. Others, shielded within denser halos or more remote locations, resisted reionization longer and contributed to star formation at later times. Understanding which clouds survived and which were destroyed is central to reconstructing the timeline and structure of cosmic reionization. This leads to the incredibly rich and complex modeling work being done today, simulating the evolution of gas clouds under a wide range of physical conditions. Modern simulations now include radiative transfer, non-equilibrium chemistry, magnetohydrodynamics, and feedback processes, aiming to replicate the birth and death of primordial gas clouds with unprecedented accuracy. These simulations are not just theoretical exercises. They are increasingly tested against real data from high-redshift galaxies and the 21-centimeter signal, refining our understanding of the early universe in real time. One of the next great challenges is to use these simulations in tandem with machine learning to extract patterns and signatures that human observers might miss. The hope is that by feeding large datasets of simulations into artificial intelligence models, we might uncover subtle correlations, perhaps between the mass of the dark matter halo and the cooling efficiency of the gas, or between the spatial distribution of clouds and the duration of metal-free star formation. As this synergy between theory and observation evolves, we are also starting to imagine the final frontiers, the last remaining truly primordial clouds, if any still exist. These would be untouched by star formation, unpolluted by metals, and unheated by reionization, a near impossibility, but not beyond the realm of speculation. Detecting such a cloud would be akin to finding a cosmic Rosetta Stone, a direct, unaltered sample of the universe's original matter. Some suggest that such clouds may linger in the outskirts of galaxies, within vast voids, or hiding within low-mass halos too small to ignite star formation. The implications of finding one would be immense. We could confirm the predictions of Big Bang nucleosynthesis with unprecedented precision, test the cooling models of molecular hydrogen without interference, and perhaps even search for the signatures of exotic physics, like variations in fundamental constants or interactions between baryons and dark matter that leave no other trace. And so, the story of primordial gas clouds continues, not just as historical footnotes, but as active players in the quest to understand the deepest workings of the cosmos. They are the seedbeds of light, the architects of galaxies, and the silent recorders of the universe's infancy. In every galaxy, every star, and every atom of life on Earth, there echoes a distant memory of a time when all that existed were these silent, formless clouds drifting through a young and expanding universe. Their transformation is not merely a tale of astrophysics, it is the cosmic story of becoming. And in the final threads of their evolution, primordial gas clouds did not merely disappear, they were transfigured. Transfigured into stars, into galaxies, into the complex tapestry of cosmic structures we see today. But in their transformation, they left behind whispers, observable echoes that we continue to chase through time. From the first photons they helped unleash to the lingering 21 centimeters emissions that ripple faintly across the cosmic void, these clouds are not relics of the past. They are active messengers from the dawn of everything. One of the most tantalizing pursuits in modern astrophysics is the direct detection of the 21 centimeter signal, an ultra-faint wavelength of light emitted or absorbed by neutral hydrogen as its electron flips its spin orientation. During the epoch before reionization, this signal was one of the only beacons emitted by the cold, dark universe. Mapping this radiation would be akin to creating a three-dimensional atlas of where primordial gas clouds lived, how they moved, how they clumped, and how they vanished into stars and galaxies. Projects like EDGES, LOFER, Hera, and the Future Square Kilometer Array are racing to uncover this ancient glow. In 2018, the EDGES experiment reported a potential detection of an absorption feature in the 21 centimeters line from around 180 million years after the Big Bang. Though controversial and not yet confirmed, this potential signal sent shockwaves through the astrophysical community. Why? Because the depth of the absorption was unexpectedly large, too large to be explained by standard physics. Some theorists propose that the primordial gas clouds might have been colder than expected, perhaps due to an unknown cooling mechanism, or even interactions with dark matter. Such an explanation, if verified, would suggest that primordial gas clouds were not only passive actors shaped by gravity and cooling, but also deeply entangled with new physics that we haven't yet integrated into the standard model. It's this kind of possibility that makes the study of these ancient clouds so much more than just a retrospective. They may hold the key to unlocking hidden layers of reality itself. And it doesn't stop at dark matter. Some researchers have proposed that if primordial magnetic fields existed in the early universe, they could have influenced the collapse behavior of gas clouds. These magnetic fields, if sufficiently strong, might have resisted gravitational contraction or redirected inflows, leading to anisotropic structures and shaping the angular momentum distribution of the first galaxies. Observationally, such effects are subtle, but models incorporating them predict distinct morphologies in high redshift structures, something astronomers are just beginning to probe with instruments like JWST. Furthermore, there's a growing interest in quantum gravity effects and how they may have subtly influenced the initial conditions for gas cloud formation. For example, fluctuations at the Planck scale might have been stretched during inflation, seeding the universe with extremely faint imprints that later influenced gas dynamics in ways we don't fully understand. If this speculation holds, then primordial gas clouds might be responding not just to classical forces, but to the quantum memory of the cosmos itself. Even within known physics, there are open questions about the precise balance of cooling and heating mechanisms within these clouds. While hydrogen and helium dominated their composition, the efficiency of cooling through molecular hydrogen formation could have varied greatly. The presence of Lyman-Werner photons, those capable of breaking molecular hydrogen apart, would have acted like a cosmic thermostat, regulating when and where clouds could actually cool enough to collapse. Understanding the spatial distribution of these photons during cosmic dawn is crucial. A slight imbalance could have determined whether a particular gas cloud gave birth to a brilliant population 3-star or remained dormant in silence for hundreds of millions of years. And speaking of population 3 stars, the ultimate offspring of primordial gas clouds, we continue to seek direct observational evidence of their existence. These metal-free, ultramassive stars likely lived short, explosive lives, enriching their surroundings with heavier elements and laying the foundation for all future stellar generations. While we've yet to detect a population 3 star in isolation, their indirect fingerprints, seen in the chemical abundance patterns of second-generation stars, are being uncovered. Some stars in our Milky Way halo exhibit abundance patterns that suggest they formed from gas clouds enriched by just 1 or 2 massive POP3 supernovae. It's poetic in a way. These modern stars, glowing in our telescopes, are the descendants of gas clouds that lived more than 13 billion years ago, preserving in their very atoms a snapshot of the universe's first breaths. It shows us that even though primordial gas clouds themselves are long gone, their cosmic legacy continues, carved into the DNA of every star, every planet, every life form. Ultimately, the story of primordial gas clouds is more than just a scientific narrative. It's a metaphysical meditation on origin. From formlessness came form. From cold, quiet simplicity came the roaring furnaces of starlight. From hydrogen and helium, born in the crucible of the Big Bang, emerged the building blocks of galaxies, of chemistry, of biology, and of consciousness. So when we look up into the night sky and see the shimmer of a distant galaxy, we are not just seeing light. We are witnessing the echo of clouds, clouds that never saw stars, that never knew structure, that simply obeyed the ancient rules of physics, collapsing and cooling and igniting the very fabric of what we now call the universe. They remind us that from the most basic ingredients, from silence and darkness and dustless voids, can emerge complexity, beauty, and life itself. And in that quiet grandeur, the primordial gas clouds leave us with one more haunting truth: we are made of their ashes. The atoms that form your eyes, your hands, your thoughts, each began their journey in those ancient clouds of hydrogen and helium. And in a sense, those clouds were not simply cradles of matter but midwives of identity, the original sculptors of all structure, energy, and experience in our universe. As we press further into the future with space telescopes, ground-based observatories, and even lunar or interstellar probes, the quest to observe these clouds directly intensifies. Their elusive nature, their silence across much of the electromagnetic spectrum, makes them perhaps the most difficult objects in the cosmos to study. And yet they are everywhere in the early universe, filling it, flowing through the filaments of the cosmic web, waiting for gravity to tighten its grip and for time to draw them into destiny. But what if we could recreate them? In theoretical astrophysics, there is growing interest in using extremely high-resolution cosmological simulations, in the trillions of particles, to replicate the earliest epochs of structure formation, including the life cycles of individual gas clouds. These simulations attempt to model the turbulent interplay of gravity, radiation, gas dynamics, and even chemistry, tracing how a single overdensity in a sea of primordial hydrogen eventually births the first star. In essence, it allows us to build digital replicas of the early universe, virtual gas clouds, that behave just as their real counterparts did over 13 billion years ago. What makes these simulations so awe-inspiring is not just their scientific precision, but their philosophical depth. They allow us to watch the universe imagine stars for the first time, to see how raw chaos folds into light, how formlessness finds identity. They give us not only data, but understanding. And that understanding reverberates far beyond the realm of science. It speaks to our deepest questions about origin, purpose, and fate. Indeed, as we consider our own origins, how Earth, life, and intelligence came to be, we cannot escape the reality that everything is downstream from these primordial clouds. The oxygen in our lungs was once forged in the heart of a star, but that star's own birth depended on the collapse of a gas cloud that, in turn, was sculpted by ancient physics acting on material that had never before been part of anything. We are the latest note in a cosmic song that began with the first whisper of hydrogen cooling into silence. Yet there are still countless unanswered mysteries. For instance, how exactly did the transition from population 3 to population 2 stars occur across the universe? Was it gradual, or did regions switch from metal-free to metal-enriched abruptly, triggered by local supernova feedback? Were there intermediate, strange classes of stars that no longer exist? Could some pockets of metal-free gas still remain uncollapsed, lurking in cosmic voids, waiting to be discovered? These are not idle curiosities. they speak to the very architecture of cosmic evolution. And what of the possibility that primordial gas clouds seeded the conditions for life more directly than we imagine? Though they themselves lacked metals, the stars they birthed eventually exploded into space, seeding heavier elements. Could these explosions have occurred in just the right environments to preserve complex molecules? Could early clouds near certain gamma-ray bursts or supernovae have briefly created warm, enriched zones in the intergalactic medium, strange, fleeting islands of chemical potentiality? It's speculative, yes, but entirely plausible, and such ideas are beginning to inspire new models of astrobiological emergence. Moreover, the role of chaos and symmetry in primordial gas cloud evolution is another layer of profound depth. These clouds formed from perturbations in the cosmic density field, slight asymmetries in an otherwise smooth universe. But those asymmetries, minuscule, quantum-scale fluctuations from the inflationary epoch, would eventually define the fate of galaxies, clusters, and black holes. In that sense, a primordial gas cloud is the first canvas on which quantum mechanics and gravity painted something permanent. The randomness of a vacuum fluctuation 13.8 billion years ago might have determined the formation of a gas cloud, which then collapsed into a star, which later exploded and scattered the calcium that now makes your bones. That is not just science, it's existential poetry. Even more breathtaking is the emerging possibility that some primordial gas clouds never collapsed at all. If dark matter halos failed to accrete enough gas, or if feedback radiation from nearby structures was too strong, these clouds may have remained as ghostly reservoirs of neutral hydrogen, still cold, still intact, still untouched after all these billions of years. If such clouds exist today, they may be hiding in voids or cloaked in low surface brightness, and discovering one would be among the most extraordinary achievements in observational cosmology. But even if we never see one directly, the idea that they're still out there, drifting in the deep dark, unmoved, unspoiled, is enough to ignite a sense of cosmic reverence. These would be the oldest untouched things in existence, predating every galaxy, every star, every planet. To find one would be like uncovering a fossil from before the beginning of time. Ultimately, the story of primordial gas clouds is not just a story of matter. It is a story of cosmic potential, a tale of waiting, of becoming, of ignition. It reminds us that even in the darkest silence, even in the emptiest cold, there is the capacity to evolve into brilliance. The universe was not born in fire, it was born in gas, in cloud, in stillness. And from that stillness came everything. So as you look up tonight at the endless stars, remember this: somewhere beyond that light, in a silence deeper than time, once floated a simple cloud of gas. It had no structure, no metals, no complexity. But it had potential. And from that potential came all the light that ever was. And now, as we turn toward the future of cosmic discovery, we realize that the journey to understand primordial gas clouds is far from over. In fact, we are just beginning to uncover their deepest secrets. As our telescopes reach farther back in time, piercing the veil of the universe's first few 100 million years, we inch closer to directly witnessing the very processes that these clouds set in motion. But more than mere observation, we are also beginning to recognize that the evolution of primordial gas clouds might not be uniform across the cosmos. Their behavior, their collapse, and their role in star formation could have varied drastically depending on local conditions, temperature, dark matter halo mass, and proximity to the first energetic sources of radiation. This introduces the idea of cosmic variance in the early universe, where different regions, even at similar epochs, underwent unique evolutionary tracks. One primordial cloud in a dense filament might have collapsed rapidly and birthed an entire cluster of stars. Another, isolated in a vast void, might have remained dormant for millions of years. This randomness, this unpredictability, means that the early universe may have been a mosaic of contrasting environments, bright stellar nurseries adjacent to dark, undisturbed gas fields. It's here that the hydrodynamics of cosmic evolution becomes critically important. To truly understand how these gas clouds behaved, we must model not just their gravitational interactions but also their internal thermodynamics, how energy moved through them, how turbulence affected fragmentation, and how rotational dynamics created spin that seeded early angular momentum in protogalactic disks. These are nonlinear, chaotic processes, and they may have been sensitive to minute variations in cosmic conditions, such as the relative streaming velocities between dark matter and baryonic gas after recombination. This last concept, baryon dark matter velocity offsets, is a relatively new realization in cosmology. After the universe recombined, baryons, normal matter, and dark matter did not move in perfect harmony. The result? Some regions experienced delayed gas collapse because baryons couldn't settle into dark matter halos as easily. In such regions, primordial gas clouds may have formed later or differently, or not at all. This subtle effect, embedded in the universe's first movements, might have profoundly influenced the large-scale structure we see today. Now imagine the implications of all this. The Milky Way, the solar system, Earth itself, may all owe their existence to the specific history of a primordial gas cloud that just happened to collapse early, or efficiently, or under ideal conditions. Every galaxy we see may have emerged from a unique chain reaction of collapses and enrichments, originating from clouds that drifted in the void billions of years ago. And some of those clouds may still be out there, untouched and invisible, waiting to be discovered with the next generation of observatories. But we are not just content with theory. In the coming decades, instruments like the Square Kilometre Array, SKA, will map the neutral hydrogen of the universe in unprecedented detail. These surveys will attempt to trace the 21-centimeter line of hydrogen from epochs as early as 100 million years after the Big Bang. If successful, we will be able to see the outlines of the very first primordial gas clouds, cold shadows against the backdrop of the cosmic microwave background. We will, for the first time, watch the universe wake up, one cloud at a time. Moreover, there's rising excitement over gravitational wave astronomy and its potential to reveal signatures from population 3-star collapse. If massive enough, these stars may have formed binary systems that collapsed into black holes, merging billions of years later and emitting gravitational waves. If we can trace such a signal back to a time consistent with primordial star formation, we gain indirect insight into the mass spectrum and formation conditions of the very clouds we've been discussing. And in perhaps the most speculative but profound leap, some theorists suggest that studying primordial gas clouds might help us constrain the nature of dark energy itself. If the formation rate and spatial distribution of early gas clouds can be measured with high enough accuracy, discrepancies in those patterns could indicate variations in the cosmic expansion rate across time. That, in turn, may hint at changes in the properties of dark energy, a force that remains one of the greatest enigmas in modern physics. So we return to the beginning, not of stars, not of galaxies, but of potential. The primordial gas cloud is more than just an ancient object. It is a symbol, a vessel of what could be, a quiet, undisturbed reservoir from which entire cosmic tapestries unfurled. In the silence of the early universe, where no star had yet shone and no planet had yet spun, these clouds were the only story being written, a narrative of silence destined to become the roar of starlight. When we speak of them now, we do so with reverence. Because in those clouds, we find not only the origin of structure, but a metaphor for ourselves. We too are clouds of potential. We too begin in darkness, shaped by forces we often don't understand, waiting for the right moment to collapse inward, to ignite, and to shine. From chaos and simplicity, from silence and symmetry breaking, the universe built worlds. And it began, always began, with a cloud. Yet as we stand on the threshold of deeper cosmic comprehension, we must also confront the limitations of our current instruments, models, and perspectives. For all we know about primordial gas clouds, the vast majority of their history is still shrouded in observational darkness. The light they did not emit, the silence they kept, and the timelines they followed are all embedded in the structure of the cosmos. But teasing out that history requires instruments capable of listening to the quietest whispers of the universe. The coming age of astronomy, therefore, is not one of merely seeing brighter or farther. It is one of decoding the invisible, of learning to read the faint traces that primordial gas clouds etched into the intergalactic medium. These traces include subtle anisotropies in the cosmic microwave background, minute temperature deviations, patterns in the distribution of Lyman alpha emitters, and even interferometric silhouettes in deep 21 cm maps. They are not loud clues, they are faint signatures hidden within cosmic static. But like a paleontologist reconstructing a dinosaur from a single tooth, astronomers are becoming adept at building entire epochs from the faintest remnants of ancient gas. And those remnants do more than illuminate our past. They challenge us to rethink the evolution of structure altogether. One of the more radical shifts in recent years is the growing suspicion that primordial gas clouds may have formed around exotic scaffolding. Beyond dark matter halos, theorists have explored the notion that topological defects, like cosmic strings or domain walls, predicted by early universe physics, could have locally enhanced gravity, drawing in gas and triggering early collapse. Though entirely speculative, such structures would produce unique patterns in cloud distribution, and might even explain anomalies in large-scale structure or CMB cold spots. In that same spirit, some researchers have suggested that primordial gas clouds could have formed mini black holes, rather than stars, in especially dense regions. If the collapse occurred too quickly, before angular momentum or turbulence could fragment the cloud, the result might be a direct gravitational implosion into a black hole. These primordial black holes have been proposed as possible dark matter candidates, and could offer a radically different path from gas to gravity, one that bypasses starlight altogether. That possibility introduces an even more profound tension in cosmology, that not all clouds became light, and that some of the universe's earliest matter may have sunk invisibly into gravity wells so compact, so dark, that they contribute only to mass and never to illumination. These black holes could still be wandering today, millions, even billions of them, silent relics of a phase of the universe we can barely imagine. And then there's the idea that not all gas clouds evolved in isolation. In many cosmological models, multiple clouds could converge, collide, or compress under mutual gravity, forming larger protogalactic structures. These early mergers may have led to giant starburst events, where hundreds of thousands of massive stars formed almost simultaneously, creating explosive waves of radiation and chemical enrichment. Such events would have dramatically reshaped the surrounding space, blowing out ionized bubbles and sowing the first seeds of galactic identity. Even today, massive ellipticals and spiral galaxies carry within their structure the chaotic fingerprints of those early clouds. The angular momentum of a spiral galaxy, for instance, may have its roots in the spin of the primordial gas clouds that merged to form it. And galaxy clusters, those vast metropolises of matter, can trace their ancestry back to entire filaments of coalescing gas, each cloud a chapter in a narrative that would take billions of years to reach its modern form. This is perhaps the most awe-inspiring insight of all, that the structure of the universe is not a coincidence. It is the consequence of clouds. The stars we see, the galaxies we map, the voids we chart, these are all the result of how primordial gas clouds behaved under pressure, heat, and gravity. Whether they fragmented or coalesced, heated or cooled, absorbed or radiated, their choices, governed by physics, wrote the architecture of reality. And this architecture, despite its elegance, was forged in the crucible of cosmic struggle. Gas clouds did not form in peace. They were torn by shocks from nearby supernovae, bathed in Lyman-Werner radiation, buffeted by gravitational tides, and in many cases, erased by early reionization. They were survivors, ephemeral, vulnerable, but vital. Some collapsed into the first stars. Some vanished without legacy. Some held out long enough to influence the formation of supermassive black holes, perhaps by collapsing directly under rapid accretion. Even the enormous black holes at the centers of galaxies, millions or billions of solar masses strong, may owe their origin to the most massive primordial gas clouds. In regions of extremely rapid inflow, with minimal fragmentation and strong UV suppression of molecular hydrogen, it's thought that clouds could have bypassed normal star formation entirely and collapsed into direct collapse black holes. These then grew via accretion and mergers, becoming the dark hearts of the galaxies we see today. So in a very real way, primordial gas clouds are the authors of destiny. They determine not only what forms, but what does not. Where there is silence in the universe, where stars did not form, where voids stretch across tens of millions of light years, there, too, is the signature of gas clouds. For absence is not random. It is the other side of structure. It is the space left behind by choices made in the earliest epochs of time. And as we end this chapter in our meditation on the primordial clouds, we are reminded of something deeply personal. That we, humans, thinkers, dreamers, are not observers separated from this story. We are part of it. The hydrogen in your blood, the carbon in your brain, the calcium in your bones, all of it began in the stars, but those stars began in clouds. To understand those clouds is to understand ourselves, not in metaphor, but in matter. They were the first canvases of creation, the first outlines of form, the first stirrings of energy shaped by entropy. They were not stars. They were not galaxies. They were potential, floating across a dark and silent universe, waiting to collapse into something more. And from that collapse, the cosmos became awake. Even now, as we probe deeper into the fabric of the cosmos, the legacy of primordial gas clouds remains central to virtually every branch of astrophysics and cosmology. These clouds did not merely exist at the dawn of time, they established the initial conditions for every cosmic process that followed. They determined the locations of the first stars, the early abundance of heavy elements, the morphology of galaxies, and the scaffolding of large-scale structure. In short, they laid the blueprint for the universe we inhabit today. Yet their influence stretches even further than structure. It reaches into the very chemistry of life. The early stars formed from these clouds, the population 3 stars, forged the first elements heavier than helium in their cores. When these stars exploded as supernovae, they seeded their surroundings with carbon, nitrogen, oxygen, and iron, the raw materials necessary for life. Those elements, swept into newer clouds, eventually found their way into stars like our Sun, planets like Earth, and into you. Without primordial gas clouds acting as the cosmic womb, life as we know it would not be possible. Their silence gave birth to sound. Their darkness gave birth to light. Their simplicity gave birth to complexity. But we cannot reflect on this epoch without also acknowledging the staggering scale of time and space involved. These clouds formed more than 13 billion years ago, across distances that defy ordinary comprehension. A single gas cloud might have spanned hundreds of light years and contained the mass of thousands of suns. Yet to the universe at large, it was still a minuscule dot, an unnoticed fluctuation in an expanding void. That something so seemingly small could give rise to all that we see is a testament to the incredible power of nature when guided by the laws of physics. And the laws that shape these clouds, gravity, thermodynamics, hydrodynamics, quantum mechanics, and particle physics, interacted in elegant yet unpredictable ways. A fraction of a degree in temperature, a slight variation in density, or a minor fluctuation in radiation intensity could decide whether a cloud collapsed, fragmented, or dissipated. These minute variations acted as cosmic coin tosses, each determining the fate of billions of future stars and planets. In this way, the universe became a grand experiment, one whose initial conditions were etched into the cold hydrogen of primordial clouds. Our understanding of these clouds, though still emerging, has been accelerated by some of the most ambitious simulations ever performed. Projects like Illustris, Eagle, and Renaissance have attempted to model the universe's formation from its first moments to the present day. These simulations incorporate billions of particles representing gas, dark matter, and stars, evolving over cosmic time within a computational framework that captures gravity, radiation, star formation, and feedback processes. In these models, we can watch primordial gas clouds take shape, collapse into stars, and ignite the first epochs of cosmic light. We can rewind the clock, change the parameters, and see what the universe might have become under slightly different circumstances. And those simulations often yield surprising results. Some show that star formation in the early universe was more chaotic than previously believed, with intense feedback from supernovae constantly disrupting cloud formation. Others suggest that certain primordial clouds may have lingered in isolation, surviving reionization and remaining pristine for billions of years before forming stars, offering potential observational targets for telescopes like the JWST. Still others hint that the first galaxies might not have looked like galaxies at all, but rather diffuse, faint blobs of stars loosely bound by dark matter and shaped by the chaotic collapse of gas. In this context, primordial gas clouds are not static entities. They are dynamic actors in a vast, interconnected system. They feed galaxies. They absorb and radiate energy. They grow, collapse, fragment, or evaporate. They respond to their environments, and in turn, shape those environments for everything that comes next. The dance of these clouds across the early universe is like a cosmic symphony, sometimes dissonant, sometimes harmonious, always evolving. And yet, despite all this complexity, the core mystery remains. What exactly triggered the collapse of the very first cloud? Was it a purely gravitational process? Was it aided by cooling from molecular hydrogen? Was it nudged by interactions with dark matter filaments or early turbulence? Or could it be that the universe had multiple pathways to star formation, some we haven't even imagined yet? The answers remain elusive, hidden in data we've yet to collect and light we've yet to see. And therein lies the excitement, the unknown. Primordial gas clouds sit at the edge of discovery, a veil just beginning to lift. Every new telescope, every new observation, every refinement in our simulations brings us closer to seeing them clearly, not just as theoretical constructs, but as tangible parts of cosmic history. They remind us that the universe is still writing its autobiography and that we, in our pursuit of knowledge, are privileged to read its earliest pages. But perhaps the most poetic truth of all is this, that these clouds, cold and silent though they were, are not gone. Their remnants survive in the interstellar medium, in the faint wisps of gas between galaxies, in the low metallicity clouds that drift across the Milky Way. We may even be able to detect fossil clouds, unchanged pockets of primordial gas, if we look in the right direction, at the right wavelength, with the right technology. And so, the story continues. Primordial gas clouds are no longer merely ancient relics. They are active participants in our quest for meaning. They are the storytellers of the universe, holding the secrets of beginnings, endings, and everything in between. To study them is to understand the cosmos. To understand the cosmos is to understand ourselves. And all of it, every star, every galaxy, every being, started with a cloud that once drifted silently through the darkness, waiting to ignite the light of everything. But even as we inch closer to these profound truths, the veil of mystery remains tantalizingly intact. The vast silence of the early universe still echoes with unanswered questions. What happened in those brief instants between the decoupling of light and the first gravitational collapse? How long did the primordial clouds wander the void before gravity sculpted them into something more? Were there entire populations of clouds that never birthed stars, never grew luminous, and instead dissolved into the intergalactic medium, forgotten actors in the theater of creation? It is these possibilities, the unseen stories, the unlit pathways, that continue to inspire new generations of astronomers and cosmologists. The early universe is not a closed book, it is an open field of exploration, with primordial gas clouds scattered like ancient ruins waiting to be excavated. These clouds, fragile and immense, may hold clues to other puzzles as well, to dark matter, to inflation, to the very reason our universe appears fine-tuned for complexity. Consider, for example, the tantalizing concept that primordial gas clouds could have behaved differently in a slightly altered universe. In a universe with slightly weaker gravity, perhaps the clouds would never have collapsed at all, and the cosmos would have remained forever dark, forever cold. In a universe with slightly stronger gravity, clouds may have collapsed too quickly, forming only massive black holes and bypassing stars entirely. These what-ifs are not just speculative, they are essential to our understanding of why this universe, the one we inhabit, looks and behaves the way it does. And the answer may lie, at least in part, within the clouds themselves. By analyzing the distribution and properties of primordial gas, cosmologists can put constraints on the values of fundamental constants and the behavior of physics at high energies. This kind of investigation may lead to breakthroughs not only in astrophysics but in the very foundations of particle physics and quantum theory. For instance, variations in the fine structure constant, or the behavior of dark energy during the era of gas cloud formation, could imprint themselves in subtle ways on the early clouds' collapse timelines. Then there is the ever-deepening mystery of dark matter's role. While primordial gas clouds were made of ordinary matter, hydrogen and helium, those clouds were influenced, even shepherded, by the gravitational pull of dark matter. In fact, without the presence of dark matter halos, it is doubtful that gas clouds could have coalesced and cooled quickly enough to begin star formation within the age constraints we observe. The dark scaffolding of the universe gave structure to the luminous narrative we now trace. But dark matter itself remains invisible, undetectable except through its effects. Thus, in tracing the history of gas clouds, we simultaneously map the shape of something we cannot yet define. They are the fingerprints of an invisible hand. And the intrigue doesn't end there. As observations push deeper, using quasar light to probe hydrogen absorption at extreme distances, using the 21 cm hydrogen line to map cosmic dawn, using gravitational lensing to uncover otherwise hidden structures, we are beginning to suspect that primordial gas clouds may also tell us something about the nature of time itself. The way these clouds evolve, interact, and collapse could reveal whether time is truly uniform across the universe, or whether subtle distortions exist, driven by unseen forces or dimensions. Could it be that the clouds near the earliest known galaxies experienced a slightly different rate of evolution than those forming in quieter, more isolated regions? Could the process of reionization, once believed to have been relatively uniform, actually have unfolded in a wildly chaotic mosaic, where some clouds were obliterated while others survived untouched for eons? These questions push at the boundaries of not just astrophysics but of cosmic philosophy. What does it mean for something to be primordial? Does it imply purity? Simplicity? Or does it represent the unknown, the unmeasured, the origin point beyond which we cannot see? In this sense, primordial gas clouds are more than scientific subjects, they are cosmic metaphors. They embody the paradox of beginnings, how nothingness gives way to somethingness, how cold becomes warmth, how silence gives way to song. The deeper we study them, the more they teach us about beginnings, not just of stars and galaxies, but of structure, memory, causality, and the very idea of progress in a universe without direction. Their quiet floating presence in the early universe, before time had rhythm and light had texture, is a reminder that sometimes, it is the waiting that gives meaning to the unfolding. That perhaps the most important transformations are the slowest, the most invisible. And so, our gaze returns to the cosmic seas of the past, where clouds of gas drifted under the influence of invisible forces, cooling slowly, collapsing eventually, igniting finally. Each one of them was a seed, planted in an unfathomably large void, from which an entire stellar ecosystem would blossom. Some of those stars would burn hot and die young, creating supernovae that spread metals across galaxies. Others would become red dwarfs, quietly burning for trillions of years, longer than the universe has yet existed. Among the vast multitude of clouds, only a few would ever directly contribute to planets, biospheres, or civilizations. Yet without all of them, the collapsed, the evaporated, the silent, none of those things could exist. That is the lesson of the primordial cloud, that creation is cumulative, that the universe is a symphony of interdependence, and that even the most insignificant moment, like a gas particle drifting for 1 billion years, can be foundational. As we build newer telescopes, dream up more powerful simulations, and refine our cosmological models, we are not just probing data. We are reading an ancient language. The grammar is thermodynamics. The alphabet is hydrogen. The stories are coded in light, shadow, and silence. And the authors, long gone, were the clouds themselves. Primordial gas clouds do not speak in words, but in structure. They tell us how the universe grew from chaos into complexity. They whisper of collapses so vast that they reshape time itself. They remind us that everything we know was once only potential, suspended in stillness, waiting for the spark. And we, in our restless curiosity, are the children of that spark. It is humbling to recognize that every breath we take, every heartbeat we feel, and every thought that passes through our minds is, in some poetic sense, an echo of a primordial gas cloud. The hydrogen in our water, the oxygen in our lungs, the carbon in our cells, all of it was forged in stars, which themselves were born from clouds of ancient, formless gas. We are not separate from the cosmos. We are a continuation of its earliest whispers, the conscious expression of a process that began over 13 billion years ago in utter silence. The story of primordial gas clouds is not only about astronomy, it's about origin, not just the origin of matter, but of structure, complexity, and ultimately, awareness. When we trace the formation of the first hydrogen clouds, we are really peering into the conditions that made it possible for galaxies to exist, for planets to form, for life to emerge, and for minds to wonder. The mystery of these clouds is therefore also a reflection of the mystery of ourselves. These clouds existed before galaxies, before time had structure, before light had shape. They existed when the universe was a dark, smooth ocean of possibility, when entropy had not yet carved valleys of difference into the terrain of time. But it was precisely these clouds, pulled by gravity, cooled by expansion, agitated by quantum fluctuations, that broke the symmetry of that stillness. They were the first tremors of difference in a sea of sameness. And from that difference came everything. What fascinates cosmologists most is the elegant fragility of this cosmic balance. If the early universe had slightly more energy, the clouds may have dispersed too quickly to ever collapse. If it had slightly less, the universe might have recollapsed before stars could form. It's as though the universe was fine-tuned, perhaps naturally, perhaps by some deeper mechanism, so that clouds could exist long enough, in the right conditions, to begin the long journey from gas to galaxy to consciousness. But we must also confront the reality that most of these clouds never became anything more. Many of them drifted for hundreds of millions of years, warmed slightly by the first starlight, then ionized and destroyed by the cosmic dawn. Others were pulled into forming galaxies and torn apart before stars could form. Some collapsed too quickly and formed stars so massive that they exploded within mere millions of years, spreading their atoms into space and preventing further star birth. In this sense, the primordial gas clouds are also a story of failure, of unfulfilled potential. Yet it is precisely from these failures that the raw material for success was born. Our own Milky Way galaxy, spinning serenely in the night sky, is the product of countless such stories. The gas that made our sun once drifted anonymously through intergalactic space. It might have passed through regions dense with dark matter, been shaped by ancient magnetic fields, and been ionized by powerful bursts of ultraviolet radiation from the first quasars. All of that history, written in temperatures, densities, and flows, culminated in a small region of gas collapsing 4.6 billion years ago to form the solar system. And here we are now, tracing that journey backwards, attempting to understand how the invisible scaffolding of hydrogen evolved into the vibrant architecture of stars and planets. This is why the study of primordial gas clouds is more than just a footnote in cosmology. It's the seed from which the tree of cosmic structure grows. Observing and modeling these clouds is not only about measuring redshifts and densities. It's about looking back into a time when the universe first learned how to breathe, how to shine, how to be. And yet, despite their importance, these clouds are some of the most elusive objects in all of astronomy. They are not visible with ordinary telescopes. They emit little to no light. Their signatures must be inferred indirectly, through absorption features in the spectra of distant quasars, through radio signals at the 21 centimeters wavelength, or through the imprint of their behavior on the cosmic microwave background. These are faint fingerprints left in cold places, written in languages we are only beginning to decode. The 21 centimeters line, in particular, holds incredible promise. Generated by the hyperfine transition of neutral hydrogen atoms, this signal offers a direct probe of the gas that existed between the recombination epoch and the epoch of reionization. Through it, we hope to create the first true three-dimensional maps of the early universe's hydrogen distribution. Instruments like LOFAR, the Square Kilometer Array, SK, and the Hydrogen Epoch of Reionization Array, HERA, are being developed to decode these whispers. If successful, we will be able to visualize the evolution of primordial gas clouds across time, watching them collapse, merge, fragment, and disappear, all without ever seeing a single star. The promise of such a capability is nothing short of revolutionary. Imagine being able to rewind the cosmic clock, not in imagination or theory, but in direct observation. To watch the first clouds drift, to observe their collapse, to witness the birth of the first star from the cold ashes of a once homogeneous cosmos. It would be the ultimate form of cosmic archaeology, a way to uncover not just our origins, but the origin of structure itself. And still, questions multiply. Did primordial clouds form in isolation, or were they always influenced by their cosmic neighborhood? Were they regulated by feedback mechanisms from early stars and black holes, or did some regions escape this disruption entirely? Could there be clouds today, hidden, untouched, preserved in dark corners of the universe, waiting to be discovered? If such relic clouds exist, they could offer the clearest window into the original state of the universe's baryonic matter. Studying them could reveal the true primordial composition of the universe, test predictions from Big Bang nucleosynthesis, and even constrain exotic phenomena like the decay of dark matter particles or the effect of hidden fields in early inflation models. The primordial gas cloud is no longer just a chapter in the book of the cosmos. It is the preface, the ink, and the parchment itself. To understand it is to understand how creation unfolded, molecule by molecule, fluctuation by fluctuation, until light filled the void and complexity was born. And we are only at the beginning of this understanding. Every observation brings new mysteries. Every model reveals new questions. The primordial gas clouds are still speaking, and we are still learning how to listen. These clouds, vast, frigid, and ancient, are silent witnesses to the most profound transformations in the cosmos. While stars burst with light, and galaxies dance in spirals of brilliant structure, the primordial gas clouds lingered in darkness, undisturbed and uncelebrated. Yet it was their stillness, their latent potential, that made everything else possible. Before there were galaxies, before there were clusters, before even the first starlight flickered into existence, there was only this, hydrogen and helium, suspended in a newborn universe, slowly and silently assembling under the invisible hand of gravity. To truly grasp the scale and strangeness of these clouds, consider their physical dimensions. A single primordial gas cloud could stretch across hundreds of thousands of light years, far larger than most modern galaxies. But within that volume, the matter was unimaginably sparse, so diffuse that you would find only a few atoms per cubic meter. In our daily experience, such low densities are inconceivable. Yet this is where the cosmic story began. In a sea of almost nothing, stretched thin by cosmic expansion, drifting between patches of slightly more and slightly less density. It was in those barely denser regions that the future took root. And that density variation wasn't random. It was seeded by tiny quantum fluctuations, amplified by inflation in the earliest moments of time. What began as microscopic ripples, uncertainties in the fabric of space-time itself, eventually became the scaffolding on which matter gathered. These ripples, frozen into the universe by the time the cosmic microwave background was emitted, later guided the primordial clouds into their positions. Without those ripples, there would be no clouds, no stars, no galaxies, no us. We tend to think of gravity as a force that pulls things together, but in the early universe, its job was much harder. Gravity had to overcome expansion, which was pulling space itself apart at accelerating speeds. It had to work within an environment of almost perfect uniformity, where the difference between dense and less dense was minuscule. And it had to act patiently, taking hundreds of millions of years to turn the tiniest clumps into gravitational wells deep enough to begin attracting gas. The primordial gas clouds were gravity's slow triumph against entropy. But that triumph was far from guaranteed. Even after collapsing into more compact structures, the gas needed to cool in order to condense. And this is one of the most fascinating puzzles of early cosmology. How did the first clouds cool? In a universe without heavy elements, the usual mechanisms of radiative cooling, such as emission lines from carbon or oxygen, did not exist. What we now understand is that molecular hydrogen, H2, played a crucial role. Despite being incredibly inefficient compared to metals, molecular hydrogen could radiate away heat via its rotational and vibrational modes, allowing clouds to shed energy and collapse further. Yet even molecular hydrogen was rare. The early universe had no dust grains to catalyze its formation, as happens today. Instead, H2 had to form through gas phase reactions, like those involving free electrons or hydrogen ions. These processes were slow and fragile, easily disrupted by radiation from the first stars. This meant that only a select few regions, under the right conditions, could form the very first stars. These stars, population 3 stars, were unlike anything we see today. They were massive, ephemeral, and utterly unique. Formed from pure hydrogen and helium, with no metals to regulate their internal processes, they likely reached hundreds of solar masses. Their lifespans were brief, just a few million years, but their impact was profound. They emitted floods of ionizing radiation, carving out ionized bubbles in the surrounding hydrogen, and their deaths, often as supernovae or even parent stability supernovae, ejected the first heavy elements into space. This changed everything. With metals now present in the gas, cooling became much more efficient. Future clouds could collapse faster, fragment more, and give rise to a wider range of star sizes. This began the cosmic transition from the primordial to the complex, from population 3 to population 2 stars, and eventually to stars like our Sun. In this way, the history of primordial gas clouds is also the history of cosmic evolution, a slow accretion of complexity, born from the simple. But what's even more intriguing is how these clouds were not evenly distributed. They gathered preferentially in regions where dark matter halos were forming. Dark matter, unseen, undetectable directly, yet making up most of the universe's mass, served as a gravitational framework. It gathered first, drawing in baryonic matter like a web pulling dew. Where dark matter pooled, gas followed, and the earliest structures took shape. The relationship between gas and dark matter is therefore one of codependence. One gives structure, the other gives visibility. In fact, many of the first mini-halos of dark matter may have failed to ever form stars. If they couldn't accumulate enough gas, or if early radiation heated and dispersed their material, they remained dark forever. These dark halos may still float invisibly through space today, massive, present, but unseen. And if so, they are ancient ghosts of a primordial time, relics of a universe that almost was. It's also worth considering how primordial gas clouds influenced one another. Once stars began to form, their light didn't merely illuminate, it changed the environment. Ultraviolet radiation could dissociate molecular hydrogen in nearby clouds, halting star formation. Supernova explosions could trigger collapse in neighboring clouds, or disperse them entirely. The early universe was therefore not a quiet field of independent processes. It was dynamic, interactive, and surprisingly violent. Feedback effects meant that each cloud's fate was partially determined by the behavior of others. And as more clouds collapsed and more stars ignited, the universe began a slow transformation. Reionization, when the hydrogen that had become neutral after the Big Bang was reionized by starlight, was underway. This phase change, from neutral to ionized, changed the cooling dynamics of the gas. It heated intergalactic space, suppressed star formation in some areas, and permanently altered the thermal history of the cosmos. Today, scientists are racing to map this era of reionization and the clouds that participated in it. Using tools like the James Webb Space Telescope, radio arrays, and deep field surveys, we are trying to piece together the jigsaw puzzle of early structure formation. What were the shapes of the first clouds? How did they arrange themselves? Did they cluster like modern galaxies, or follow a different pattern entirely? And with each new observation, we get closer to understanding not just what happened, but why it happened the way it did. Perhaps someday soon, we will be able to simulate a single primordial gas cloud with such precision that we can trace every eddy, every shockwave, every chemical reaction from start to finish. We will know, not in myth or metaphor, but in science and data, how the universe transitioned from darkness to light. The primordial gas cloud, then, is not just a scientific concept. It is the birthplace of identity, of pattern, of meaning. It holds the preconditions for beauty, for complexity, for reflection. And though it is long gone, collapsed into stars, scattered into galaxies, it is not lost. Its story is written in the atoms of our bones, the photons of our sun, the spirals of our Milky Way. And we, observers of the sky, seekers of truth, are its living memory. As we continue unraveling the story of primordial gas clouds, one must also reflect on how remarkably these clouds influence not only the formation of structure but the very tempo of cosmic evolution. The universe, at its infancy, could have unfolded in many ways. But it is the behavior of these ancient hydrogen and helium clouds that dictated when and where the first stars would ignite, how galaxies would cluster, and ultimately how the observable cosmos would emerge with such diversity and complexity. These clouds acted not just as passive reservoirs of matter but as dynamic agents of change. For instance, as gravity slowly gathered gas into increasingly denser regions, the shape and spin of the clouds mattered immensely. Rotation introduced angular momentum into the collapsing gas, creating the early rotational dynamics that seeded spiral galaxies. Without such rotation, the galaxies we know today would not have the same beautiful, flat disks or well-formed bulges. In this sense, the quiet spin of a primordial gas cloud billions of years ago dictated the blueprint of entire galactic ecosystems. Turbulence within these clouds was another critical factor. As pockets of gas moved and collided, internal pressures and chaotic flows broke them into smaller fragments. Some fragments collapsed quickly, forming massive stars, while others lingered, perhaps never forming stars at all. These chaotic dynamics introduced diversity. Not every gas cloud followed the same path. Some became the glowing nurseries of stars, others the skeletal remains of potential unrealized. This stochastic element, random and deterministic at once, may help explain why galaxies today exhibit such an astonishing variety of shapes, sizes, and compositions. Moreover, the very nature of these clouds allowed them to bridge epochs. While the stars they created burned brightly and died in short spans, the clouds themselves could persist across billions of years. Many clouds remained largely untouched by reionization, drifting in dark, unilluminated corners of the universe, serving as hidden stockpiles of pristine material. Some were eventually pulled into galaxies to continue star formation even in later cosmic eras. Others may still exist today, cold, ancient, and largely invisible, hiding in the vast intergalactic voids where light rarely travels. Detecting such relic clouds remains one of the great challenges of observational cosmology. While we have indirect evidence of their past existence through simulations and absorption studies, capturing a direct image or signature of one would be a landmark achievement. Instruments like the Square Kilometre Array, SKA, with its unprecedented sensitivity to radio waves, may finally give us a way to peer into these shadows and glimpse the untouched hydrogen of the early universe. If successful, such a discovery would be akin to finding the unbroken fossils of the Big Bang itself. Yet even in their invisibility, these clouds have left traces. When light from distant quasars, brilliant beacons powered by supermassive black holes, travels across billions of light-years, it passes through countless clouds of gas. Each one leaves a subtle imprint on the quasar's spectrum, a fingerprint in the form of an absorption line. These lines, known collectively as the Lyman Alpha Forest, provide a detailed map of where neutral hydrogen was present in the early universe. By analyzing these features, scientists can reconstruct the large-scale distribution of primordial gas and chart how it evolved over cosmic time. This method has revealed something astonishing. The universe's early structure is not random, but filamentary. The gas arranged itself into vast, interconnected filaments and sheets, separated by yawning voids. This cosmic web, a term that describes the universe's largest-scale structure, was shaped largely by the initial behavior of primordial gas clouds interacting with dark matter. Where dark matter halos formed, gas gathered; where gas cooled, stars ignited; and where stars formed, galaxies eventually assembled. The implication here is profound. Every visible structure in the universe, every star, every planet, every galaxy, can trace its ancestry back to this gaseous webwork. And each thread of this web began as a primordial cloud drifting through a dark and silent cosmos. In addition to mapping structure, primordial gas clouds have given scientists critical insight into one of the great mysteries of cosmology: the nature of dark matter and dark energy. The way these clouds collapsed, how fast they grew, and how they resisted or surrendered to gravitational influences depends heavily on what kind of dark matter the universe contains. Cold dark matter leads to different cloud behavior than warm or self-interacting dark matter would. By studying the timelines and fragmentation patterns of these ancient gas structures, scientists can indirectly constrain the properties of dark matter itself, an otherwise invisible component that makes up most of the universe's mass. Likewise, the way these clouds expand and cluster across time also provides crucial information about dark energy, the mysterious force driving the universe's accelerated expansion. If we can understand exactly how fast and in what pattern primordial clouds coalesced and collapsed over billions of years, we can test whether dark energy has changed in strength over time. In this way, the most ancient clouds serve as time capsules, not only of matter but of the very laws that govern the cosmos. And yet, even as we piece together the science of primordial gas clouds, there remains something awe-inspiring about their story. These clouds represent the universe in its rawest form, uncontaminated, unrefined, and untouched by the complexity we now see. They are the purest expression of nature's potential, the blank page upon which all later cosmic stories were written. They existed in a universe without galaxies, without stars, without even light. A time when space itself was more silence than sound, more void than vision. And from that silence came structure. From that void came life. In a strange way, we owe our entire existence to clouds of invisible gas that once drifted through the young cosmos, unaware of the significance they held. They did not burn with brilliance. They did not illuminate the night. They simply gathered, waited, and became the wombs of creation. Our telescopes may never fully reveal their shapes. Our models may never perfectly simulate their intricacies. But in the elements of our bodies, the light of our sun, and the architecture of the sky, their legacy endures. And so, the mystery of primordial gas clouds continues. As long as we search for our beginnings, as long as we yearn to understand where everything came from, we will return to these clouds, not as distant, forgotten entities, but as the quiet architects of all that is. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.